what I'm going to talk about here today is, as you heard, a classical topic in control, how to design observers for nonlinear systems. And I will not do it in the classical way. I will do it using some modern techniques based on machine learning, physics-informed machine learning. I'm more than happy if this becomes interactive, so please stop and ask questions at any time. And if you don't ask any questions, I might ask you some questions, right? This is work done in my group over the last couple of years. Umar Niassi, currently a postdoc with us and at MIT. John Kao, who is just about to start his PhD study in Oxford. Amritam, who is on the faculty in Eindhoven, and Matthew Borot, who is a colleague at KTH. And of course, we have a couple of papers if you're interested in getting more into the details and so. This talk will be quite tutorial, so I will start the basic here. Observers, we know, are fundamental for control, right? We use them in order to design controllers when we only have part of the state available through outputs. But it's also used for many other things. Observers are used for fault detection and isolation, which is an application we actually apply these techniques to. As you know, monitoring systems and understanding when they are not working perfectly is important. We've also been dealing with similar problems when it comes to cybersecurity, detecting cyber attacks, and so on. Another area which is very popular these days is digital twins, where you try to now copy basically a bigger type of systems where you emulate the system in parallel with the system operation in order to be asking a bit more complex planning questions and other type of questions for a system, where also observers come in. I said this will be tutorial. I will go back to the basics here. As some of you know your history in control. If you're not, I hope this will be a nice overview. You all know about Kalman filter, right? And his famous papers from the 60s where he set some of the foundations for our thing. Most of you probably also know about Leuenberger, but I will go a little bit more into detail. So Leuenberger did his PhD thesis on observers. So that is what we called Leuenberger observers. Was his PhD at Stanford at the time. So he had a couple of papers on this topic. And how was Leuenberger different from Kalman? In Kalman, as you know, we want to reconstruct the full state out of the measurement. We did that in a stochastic setting and so on. When we come to Leuenberger's basic idea was to say that instead of reconstructing the whole state vector, can we think about the problem of reconstructing some linear transformation of the state vector? So that was kind of a little bit a different setting, right? And in some cases, this is enough. We don't need the whole state. So let's remind us what Leuenberger observer means. So we have a linear system, x dot equal to f of x, y equal to h of x, where x and y are state and output respectively. In the design of Leuenberger observers, what we do is that we assume that we can find a linear transform, a matrix T that transforms us from the x state to z state. And then in the Z domain, we design observer dynamics. So we designed an A and B matrix so that that dynamics that I write out there is a stable dynamics. And notice now something interesting. So if we take now the derivative of the state, thanks to that we assume that we have this linear transform. We take the time derivative of the left-hand side and the right-hand side. We end up with that z dot, or t times x dot, so t times az plus t times by should be equal to the left-hand side. If you now remove the dots, right, you end up with an equation that should be fulfilled, which looks like this. So this equation is called the Sylvester equation in mathematics, and it tells us a relationship. If we want this to hold, it tells a relationship between the linear transformation that we made and now the dynamics A and B that we imposed now on the observer. So this should be fulfilled. If it's now so that this transformation matrix T is injective, so it has a left inverse, so T dagger times T is identity matrix, then we can write out now our state, the observer state, also in the original domain x hat. It's namely so, as you see, we get the observer dynamics z hat dot equal to a z hat plus by, and then we get back again to x by now taking the left inverse there, so t dagger times z hat. So this is what Leuenberger did in his PhD thesis. And he did not only come up with these two steps, he also showed some theorems around this. So such an observer exists if and only if we have a solution to that matrix equation. So it's a very nice result, right? So yeah, similar to Lyapunov stability if you want. We have a matrix equation that we can check instead of checking the dynamics. And he proved a few other results about this. We can also write the original, so to say, the observer dynamics in the original state space x hat, and then you see we get the dynamics, which looks more like an autonomous term plus a correction term in this way. We can also do something even simpler, and if you only saw one type of Leuenberger observer, this is maybe what you saw. Of course, we can choose now the x and z dimension to be exactly the same. What happened in that case? Then T is equal to the identity matrix, and then we end up with this simple dynamics that we have here, the special case of the Leuenberger observer. Okay, so that's it about linear system. So now we go to non-linear system and we apply this idea. Then we fast forward from the 60s to the 90s. So 30 years, 40 years later, this very nice work appeared, as you see here, by Katsantzis, Kravaris, and Andreu and Pouly, who there was also something in the Russian literature about this idea. So they basically took now exactly the formulation and these two steps that I went through for linear system and applied that to non-linear autonomous dynamics. So let's do that now. So, and by the way, these are called now typically KKL observers after some of the authors of these works. So we have now a non-linear autonomous system, x dot equal to f of x, y equal to h of x. And then we do the same step again. So we say that, okay, we want to find a transformation now which transform from x state to z. This is not a linear transformation typically. We have a non-linear map T there that maps us in this way. We then design linear dynamics in the z space. So the dynamics in the z space is still the same. Z dot equal to a z plus by. And then we assume now that we can take a left inverse of that map, T of x. I call it T star now. So that would be another nonlinear map, right, typically. And then I get my observer, which is given very similar to the form you saw before, where we get back to x hat by doing the left inverse then from z. So what happened now to that nice Sylvester equation? So we can do exactly the same thing. So we have this equation, z equal to tx. Now you take the derivative of z with respect to time. And if you do that, you get this equation. So you get the partial differential equation, an equation with derivative with respect to x that should be fulfilled all the time. So this is the counterpart, so to say, to the Sylvester equation for linear system. Of course, that matrix equation is easy to solve. How do we in general solve this, this partial differential equation, also fulfilling the other condition that I showed here? It's a much harder problem. But before we get into the detail of that, let's just summarize a little bit what we have done now for, or what our, so to say, predecessor did in this paper. So we were in a low-dimensional space, if you want, in the X space. We transform us up typically to a high-dimensional space. In the high-dimensional space, we consider now linear dynamics for the observer, and then we go back again. For this to work, we have two different conditions that need to be fulfilled for this transformation T here. It should fulfill this PDE, and it should fulfill this injectivity condition here for it to work. For it to work, we actually need some additional assumption because we have nonlinear systems to deal with. So it's two assumptions I want to highlight here, which is quite typical when you deal with nonlinear observers. So one is that we want the state to stay in a compact set. So this is called forward completeness, and it's stated there as you see. So we need to assume that. We also need to assume something called backward distinguishability. What it means is that when we now are observing the output here, these two outputs need to come from different states on the other side. So somehow the observer problem needs to be well defined if you want. And it's formulated mathematically as you see here. So given that these two assumptions hold, we have this amazing result by Brevadis and co-authors just a couple of years ago. So what does it state? It states when there exists such an observer. So what does it say? So these two assumptions that I showed on previous slides should hold. Then the dimension of the Z system should be specified as the first equation. And then it was the usual one, that A should be stable and A be controllable for this linear dynamics to make sense. So under these assumptions, if they are fulfilled, then we can actually find such a transformation T. So this is quite a surprising result. But notice that it doesn't tell, and the proof of this doesn't tell how we should find such a T. So how do we find this nonlinear transformation? We can know that it should be fulfilled, but not how to find it. And let's go to an example by three giants in nonlinear control systems, Prali, Isidori, and Marconi, who did a very nice paper 20 years ago where they actually designed this KKL observer for the simplest type of system you can think about in a control class that you have taken, right? So we have a harmonic oscillator. So we have in this case a system where the position of this mass is defined is Q, and then you have, of course, the equations of the oscillator up there. Let's say now that the resonant frequency, which is a constant omega, is unknown. Then we can think about that we actually formulate this as an observer problem where we would like to observe Q and Q dot as well as omega. So that is what they did in this paper. So they formulated the nonlinear dynamics, nonlinear because now we get omega squared times Q there entering, as you see down here. So we get the nonlinear ODE that we would like to do this observation of, and we assume that we then observe as an output the position here, Q of this. And then we do exactly these two steps that you saw for the design of the KKL observer. So we design linear dynamics for the observer. In this case, the authors took particularly this diagonal dynamics, as you see up there. They come up with a transformation T. I said in general we don't have systematic ways of doing that. So they come up with this transformation, this nonlinear T, where Ti, each element, is given by this rational function up there. For that function, they can find now its inverse, or its left inverse, which is given by that complicated expression up here. And this does the job. So if you now have that, you can design your observer. And here is a couple of simulations from that paper, which shows that we can now actually observe the amplitude, we can observe the resonance frequency here perfectly. The oscillations that you see, the fast oscillation is not due to, it's due to that they injected some high frequency noise signal into this. But you see it works beautifully. The problem is now, with what I talked about up to now, is that we have, so to say, the structure of this nonlinear observer, but we don't have a method of finding T and T star. We saw from this example that even for the simplest possible system, these T and T star can be quite complicated. So we would like to have systematic ways of getting them. Notice also that even if you gave me T, it's not easy for me to invert a map, right? A nonlinear map. So I need to do that and so. And now comes in the main part of this talk. So we come up with a technique now where we approximate T and T star by a neural network. So we will now introduce a neural network, and we will train the parameter of this neural network, and they will represent T and T star, and we will then plug into this observer, and we will show that that's going to work. Okay, any questions up to now or so? Yes?
This is only existence result, right? There is no uniqueness. The operator that it exists, there is no the result that usually 2000.
Yeah, the old result is an existence result, right? Yes, yes. So you mean if there could be two different ones? Yes, yes. In general, I mean, the A and B, for instance, is not uniquely defined, right? That is you who are defining that.
If it's
Yes.
A and B, then T is going to be unique or still?
No, I don't think so, but maybe I should think a little bit more about that. But I wouldn't see why it should be unique, T in general, right? Yeah.
But uniqueness does play a role here, or just the existence is enough for you?
No, I mean, as you will see here, we will have one way of constructing this T, right? Automatically now, by approximating as a neural network. So I doubt that this in general will be unique, right? So yeah, which is a good question. Thanks. Okay, but let's get into summarize a little bit what we are up to here, right? So we have the original nonlinear system. We have the observer in the Z space, and we had a way when we go from the Z space back to X in that way that I showed over there. And we have now two types of transformation that we would like to do. we would like to go from x and z. We do that through t, but now I approximate t with t theta hat. So hat because it's an approximation, theta because that's a parameter of the neural network that I have over here. So I would like to learn this parameter theta. And then I have the inverse of t. I call that approximation for t hat star with eta. And notice that I don't base it on this map. Instead, what I do is that I train another neural network, as you will see, which represents now the inverse of the first. And I will do that. So let's go a little bit into the details of the algorithm here. And notice first that I would like the two conditions to be fulfilled, the ones that I mentioned before, that the inverse holds, as well as that PDE should hold. And the PDE should hold, that basically means that this residual that I write out here should be equal to 0. So if you want, I can compare now this input and output to that neural network and check so that that residual becomes close to 0. So in order to do this, I now go through these two steps that I have done from the very beginning. So the first step now is to find the transformation t hat theta. So for those of you who do machine learning, you recognize you typically formulate an optimization criteria that you optimize with respect to the parameters of the neural network, and then you might have some constraint that should be fulfilled. So that's exactly what is happening here now. So we have an optimization criteria. We want that z should be close now to if I did the transformation of the corresponding x. So I want this to be close over time and space. And I now minimize this criteria with respect to the parameters of the neural network, with respect to theta. And then I assume that some constraints are fulfilled. So the constraint that corresponds to that the PDE should hold, the dynamics of the original nonlinear system should hold, and that the dynamics of the observer, the linear dynamics, should hold. The second thing is then to learn that inverse map, t hat star eta. So that is now a similar cost function, but it's a different neural network now. It's a t hat star eta, right? But now I would like that the difference between x, my state, and if I took now my state, transformed it through this neural network that I trained up here, and then take the inverse of that over there. I want this to be small, and I would like that to be small with respect to the dynamics that influence this criteria. And that in this case is only the x dynamics, the original nonlinear dynamics. So this is the two steps that we are going through. And let's now also go a little bit more into the detail on how to implement, because of course we don't implement it in continuous time as you saw there in the formulation, we implement it in discrete time. So first of all, I will come back to how we generate the data sets. But just for a slide now, let's just accept that I gave you two data sets, capital X hat and capital Z hat. So these are the data sets in the X domain and in the Z domain. So basically trajectories or samples of these trajectories. Then I can formulate the losses, the differences that I have there, and I can formulate the PDE loss. And then I discretize, formulate the corresponding formula that you saw, optimization problem as you saw on the previous slide. So what I do is that I now want this to be small, the data loss should be small, and then I want the constraints to hold. So with Lagrange relaxation, I then move up this up here in the cost function, and I introduce a hyperparameter nu, as you see there. So this is how, in practice, I would now train the neural network by solving that optimization problem. And then I do the same thing now for the transformation when I go back again. So then I form the data loss for that. I form the cost function, which in this case looks like this. And then out of that, I get my second neural network up there. Yes?
I appreciate very clear talk, but I thought Z was not known.
Exactly. That's,
and so the first step, how do you get the loss?
Yes. Now it comes. Thank you for that. That's exactly what I said. So how do we actually get X and Z? X we get thanks to that we know the system, right? X dot equal to fx and y, so we can simulate it. So now let's come to exactly your question. Thanks for that.
Thank you.
So what you observed here is something which is fundamental. So since the transformation from x to z is unknown, that is what we are learning here, right? How do I know that this trajectory that I have over here corresponds to that trajectory? Because you don't know where you would start. So the answer is yes, you don't know that. But instead we use a particular trick here, namely that we know that we would like to design some stable linear dynamics for the observer. So if we just wait a little bit, we know that wherever we started in the z domain, we will converge to something which corresponds to a stable observation of a state. So what we do here in practice is that we just threw away a little bit of the data in the beginning of both the x and the z trajectory. And that is what we consider when we now look at the data. So thanks for observing that. That's a key. It's a key point, and it makes it also a little bit hard in certain type of. It's not obvious how to extend this in certain direction. But let me just summarize the procedure now. So we generate this discrete data that we have. We threw away a little bit the early part of that data, and then we do the training as I described, and then we generate new data over here, and then we train again. And when we have done that, we have ended up with the with the observers that I've shown. I might be running a little bit out of time. Okay. 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 Then maybe I have time to show. Yes. So one can now prove various things about this type of observer, how it works, and so on. One thing, of course, that is interesting is it robust or not? So how would you prove robustness? There is various ways of doing that. What we did here, as you see, is that we add some noise here, W and V, some unknown thing, and then we ask ourselves, would the estimate we get out, would that still be good? So what would we mean by that? So the estimate x hat that we get out of the observer, would that be close to the original x or not? So this is one result that we have in that paper, which shows an input to state stability bound, basically. It says that this estimation error will be small or upper bounded and bounded by some quantity, as you see here on the right-hand side. Of course, the bound on the noise pops up, but also the approximation error that we have in that inverse that we get. Of course, you could argue that this I could make small now if I make this neural network very big. But anyhow, this is how we formulate that result in the talk. Notice also another thing. So I didn't talk about how to choose A and B. So what is a good observer dynamics in the Z domain here? So how should A and B be chosen? And one thing is to formulate now a design problem choosing A and B so that certain property holds. For instance, that some properties that relates to this robustness criteria could hold. Or you can incorporate something else in that formulation if you want. Okay, so if I have time, I will then also go through a couple of examples. So we run this for a number of nonlinear oscillators, so classical oscillators in the literature, 4 of them here. So as you see on all these oscillators, they have nonlinear dynamics, second or third order dynamics. This is basically what I have gone through now, a summary of the observer design. So this is now our nonlinear oscillator dynamics. We have the output that goes into the observer. The observer is linear in this case. And the output of the first term goes now to this inverse t hat star eta that then transforms back to x hat. So now we apply this thing to these 3 systems up here. So these are some data on how, so to say, complicated neural networks we need, and it's not particularly complicated. We just use standard ReLU networks with 2 free hidden layers, and the amount of data is about 50 trajectories, and each layer has about 150 to 350 neurons. The simpler one for the earlier oscillator, the more complicated one for the Lorentz attractor. And this is what it looks like. So now we train this neural network, we train the observer using these techniques, and here what you see is now the true state trajectory in black in all these different figures, and in magenta you see the observer dynamics, and you see it works very well, except if you sit very close and look very careful, you see that in some cases in the Lorentz attractor with this spiking type of phenomena, there is some errors and so. Of course, now you should be critical. You should ask yourself, when you train this neural network, with what data did you use? So this is exactly what we are going to expose next, because in these cases we trained it on data which is close to where we are when we are then running the observers, when we're running the dynamics. So for any observer or any machine learning techniques, it's of course fundamental to understand the generalizability of it. And we can express that in the following way. We can say that, okay, I train my neural network in here. How well does it do if I use it for prediction if I'm outside this domain? And then I can just measure the distance from that and see how well it's doing. Of course, if I get further and further away, since there is nonlinear dynamics here, the error should grow, right? The question is a little bit how well it works. So this is, I will show some results. And first I will compare with a result in the literature where they use some other techniques, just to have something to compare with. So in this case, you train your neural network in this domain. You want to predict the trajectory which corresponds to this oval red curve. And you see, in this case, the green, the observation is very close to the red. If you now instead run a trajectory which is this orange one outside the training data, you see that the observation, the estimated, is quite poor. in that paper, they had some techniques to improve it a little bit. But of course, I would like to talk more about how our method performs here, and also compare it with some other techniques in the literature. So we now do exactly what you saw in that example. So here you see we trained inside this rectangle. We perform very, very well. Now when we are outside, we perform a little bit worse, but still fairly close to the original state trajectory up there. Also for the other nonlinear oscillators, it's very similar type of behavior. Of course, this is individual trajectories. Then one can compare ensembles of trajectories, and this is what happens here. So here now we look at the normalized estimation error on the x-axis, and then we have time on the y-axis. And now we can compare Monte Carlo simulations and see how well you are performing with these techniques. Okay, so that was basically what I intended to talk about. So what I have tried to do is to introduce this KKL observer from the literature, but now using physics-informed neural network kind of techniques. Notice that this is not physics-informed neural network in the sense I'm not training the system to learn some physical data here, right? Some physical dynamics. I say that I know my physical dynamics, I know the nonlinear dynamics, but then I use kind of the formulation of the machine learning problem to learn this transformation in the way that I was describing here. I showed that this seems to work pretty well. I didn't have time to go into applications, but we did something on fault detection that I mentioned before, but there are also other relevant applications. Is there anything more to be done here? Yes. I mean, one obvious thing for anyone in the audience is, but what if I have a control system now? So what about if this system have a control input? Of course, we would like to do that, but it's not obvious how to extend, but we are thinking a little bit about that. And there is also other interesting and relevant problems. So with that, I would like to thank you for your attention. Thank you.
Thank you very much. Do we have any questions?
I can speak.
Yeah.
The strong generalization capability
Yes.
for initial conditions far away from training data.
Yeah.
Does it just happen, or did you do additional trick than the one you presented here?
No, there is not really any additional trick, but what I can tell you is that, you know, when we did it in this way that I described, it's not obvious that one should do it like this, right? You can think about not doing it sequentially, but doing it iteratively. You can think about that you, instead of forming this neural network based in exactly the way I described it, you can try to, let's say, form it directly out of that and so on. So we tried a few other variants, and actually some of the literature that I cite try other variants of doing that. And it seems like, as you saw from the numerical results here, it seems like our technique is doing better than the others there. But there is no hidden, there is nothing else, so to say, than what I showed here.
I guess what I meant was,
Yeah.
is there any intuition for why this generalized well? Because machine learning in general does not guarantee generalization.
Yes, yes, absolutely. So notice that what we are doing here, I mean, even if we have all these nonlinear dynamics and so on, in the end, I'm only doing actually one, so to say, component here. I'm actually generating that component, right? I'm only generating a nonlinear map there. With this whole machinery I do. So, and with this technique, it seems like this is a good way to generate this map. And of course, you can now think about other connections to other approaches in the literature. When I'm giving this talk recently, I often get this question. I don't know if any one of you are working on Koopman, right? Koopman operators is very, very powerful and very useful. So it's known to be quite heavy on data. You need a lot of data, and so it works very well in certain circumstances and other circumstances not. One can view what I describe here as an application to Koopman, if you want, or you can say that it utilizes some very specific features of the problem, of the observer problem that we do. But as you know, in general, we have a lot of exciting things where we think about how can we map things which are hard maybe in low-dimensional nonlinear dynamics up to high dimension where things might be easier. And I think we have now started to get a collection of different problems where we can do that. And to me, what we showed here with the KKL is kind of one such thing where we can do that. Koopman is maybe more general, but it also has some drawbacks when it comes to the specifics. But that is maybe part of trying to at least comment on your questions or reflections. Thank you.
Thank you.
Yes.
In your case also, yes, basically you're collecting a lot of data, and then you're. So my question is how hard to train this, yes, and how big your data should be to get to the result.
Yeah. So this is actually as I indicated with this example here. So it's actually easy. So I mean, the neural network here is no deep and very big neural network, right? It's very small neural network in this case, very little data that we are using. Then, of course, you could now want to understand if I scale this. So let's say that I have not a complicated but still only third-order system. I have a network of oscillators, right? Maybe I want to model a part of a brain or something like that, right? Let's say I have 100 neurons of my original system, and I would like to model that, and so on. How does this method scale to represent? This we don't know, but maybe this should have been on the future work, right? So how does this method scale to larger networks? So what we have shown in this paper is that it works very well when we have this complicated classical nonlinear dynamics. We can, with quite a small neural network, get very good performance. Yeah. Thank you. Thanks. Okay. Yes. Yes.
One more question.
Yeah.
Thank you for your presentation. I just want to see your opinions. Is it possible to apply your network in the control office system?
In the what? Sorry.
Control office system.
In control affine.
Yeah, control office system.
That. Yeah. I mean, as we were talking about, right? When we now add input here, in general, if I add input to a general nonlinear system, I basically don't know how to handle that today. If you now can think about special classes of system, it might be possible to do something about it. For instance, but yeah, so we have other work where we are using, we are learning the flow function of a nonlinear system. So that if you're interested in that, please let me know and I can give you the references. But so instead of learning the parameters of a parametrization of a system x dot equal to f of x plus g of x times u or something like that, we can learn the flow function of that system in a parameterized way. And there we can handle also inputs. But inputs there, we need to classify what type of inputs. And we there consider piecewise constant, so it's kind of sample data type of control system. I'm not saying that that is going to work in this case, but I think you are into something. Perhaps if one think about certain classes of system where one can reason about how you should modify the observer in order to handle that, it could be a way forward. In general, since the input in general for x dot equal to f of x and u would move the state, right? I mean, it would be hard to see how you can deal with that in general, right? You need some sort of information about how U is entering. Yeah, thanks for the...
As I've already introduced myself and also as Tigran introduced me, I'm Astrid from the National Polytechnic University of Armenia and Center for Scientific Innovations and Education. I'll be talking about my works that I've performed during the past few years, mostly during my PhD years, and some of the projects I'm currently working with some of my colleagues, fellow colleagues. And it's on the risk-aware control of autonomous systems in uncertain environments. So let's imagine a situation where we have multiple agents in a single environment. So for example, one of the simplest examples is a highway. So suppose we are the red car here. I'm not sure if we can, I'm not sure about the pointer, but yeah. Let me try. Okay, so yeah, here we are the red car here. So suppose we are able to communicate with the other agents in the same environment. So suppose we were able to communicate with the other drivers and we got information about their future trajectories. That can be any prediction or that can be any prior trajectory they want to follow or whatever information we can get from them. And of course, these predictions can be inaccurate. Of course, they can ignore these predictions, or they can follow a different trajectory, or they can be some uncertainties in the environment that can lead them to drive in another way. So what happens if we simply follow these predictions? Of course, if there are any errors in these predictions, so for example, if there are some uncertainties, we may have a collision. So we may collide with this other agents. So what this means is that we need to have risk-aware strategies that will balance safety and also performance. Of course, performance is also very important to us because we want to arrive as fast as possible, or we want to follow all the rules of the road, etc. But at the same time, one of the most important parts in autonomous systems is safety. So this is all my talk is going to be devoted to in single-agent systems and in multi-agent systems. So what are the common approaches in the literature that deal with such situations? Of course, the most famous one is the stochastic control approach that tries to optimize the performance, expected performance, under some probabilistic uncertainties. So it usually assumes that we know the uncertainty statistics at least, or some probability distributions about the uncertainties. The other approach that is very useful and very popular is the robust control approach. What it does, it assumes that we have some uncertainties, but which are usually some bounded uncertainties, and we have no information about its statistics. And what we try to do is we want to minimize, or we want to optimize the worst case performance. And in such cases, usually we have very conservative decisions, which might not be practical. The other two approaches that I usually use in my research, the first one is the distributional robust optimization-based approach that is often met in machine learning community rather than in control community, though this years, in the recent years, there have been some works on this direction to apply distributional robust optimization in control. So what it does is, instead of just using or considering the worst case disturbances, it considers the worst case distributions. So we are using some statistical information about our distribution, but we are not completely believing this distribution. So we are considering some inaccuracies in the given distributions. And an application of such approaches, or application of all these three approaches, is the risk-aware control methods. These approaches, they usually use some formal risk metrics. And one of the most popular ones are the conditional value at risk and entropic risk measures. So what it does is we consider some some loss of safety that will measure how much we are far from safety, and we will measure this risk using some risk metric that's usually coming from some financial, from finance theory. So for let's formalize our problem, what problem we have. Suppose we have a discrete time dynamical system that can represent any type of an agent. It can be a robot, it can be some financial agent, or whatever we have. And here, of course, our states are xt, control inputs are ut, but what's important here is we have a safety constraint. So we have a function, some L function that maps, that determines whether our state is safe or not. And we say that our system is safe if L of x is non-positive. So what we try to do is we want to find control inputs that, given our current states, will find control inputs that minimize the given cost function over the given prediction horizon. But what we require is that we need to also ensure that the safety constraint is met. So for that, one of the simplest ways, one of the most popular ways, is to formulate an MPC problem, model predictive control problem. So here we try to minimize the given cost function within the given horizon, time horizon, so that the constraints of our dynamical constraints are met, our safety constraints are met, and also we have some other very simple constraints for the states and control inputs. So the most important part here is how to ensure safety when we have this safety constraint, right? The problem is, as I've already mentioned, we usually have some uncertain dynamics or uncertain environment. In this situation, having this loss of safety and having this safety constraint is not easy to satisfy. So what we do is, instead of imposing this deterministic constraint, we impose a risk constraint. So we say, okay, suppose we have this L of x, but because of our x or our L itself might be uncertain, we won't have any deterministic constraints. It makes no sense to impose the deterministic constraint. What we say is that, okay, suppose this is our loss distribution. What we can do is we can evaluate the, okay, so this is the tail distribution, right? This is the worst case part of the distribution. We say, okay, let's take the expected value of the worst case events. And this part is called the conditional value at risk. And it is quite a popular metric in robotics these days because it is able to rationally assess risk. It is a coherent risk measure. I won't go deep into the details, but it is good for evaluating it's able to rationalize rare risky events. So I guess most of you will be familiar with the idea of chance constraints. Chance constraints is basically this worst case part. Okay, it's the 1 minus alpha probability. But CVAR, it's able to measure the risk in the tail events, in the tail of this distribution. So it's the expected value of the worst case events. So how do we convert this deterministic constraint to this risk constraint? So basically, as you can see here, CVAR, the definition of CVAR, it involves a minimization problem and an expectation. Here, the expectation is with respect to the probability distribution of our loss. And our loss, it might depend, the distribution might depend on the state uncertainties itself, or it can depend on the environmental uncertainties. So now what we do is we just impose this constraint instead of the deterministic safety constraint in our MPC formulation. And this problem, we call it the risk-aware MPC problem because it's able to constrain the risk of having unsafe decisions. The good thing is if we have some samples of our uncertainties, our disturbances, or our states, it doesn't matter what kind of uncertainty we have, if we have a sample data set, so for simplicity, I just assume we have a sample data set of the loss values. Then we can, in fact, define the empirical distribution and approximate our CVAR with its sample average approximation version. So if we have some data, we can create a data-driven version of our risk-aware MPC problem. In this case, it's very easy to solve this problem. Of course, it depends on the type of the loss function we have here. If it's linear or like affine, it's very easy to solve this problem. But if it's non-linear, it's going to be a bit of troublesome problem to solve. But we've found some applications for such problems, and one of them is, okay, sorry. It's this one here. So for example, here we have a quadrotor that has to travel in this uncertain environment. So here rotations and translations of these obstacles are unknown. They, all of them are coming from some, rotations are coming from uniform distribution and translations are coming from Gaussian distribution. And as you can see here, for different number of samples, we are able to safely get to our goal location. So here the blue, the black trajectory is a planned trajectory that's planned using RRT star. As you can see, we are able to safely follow the given trajectory while avoiding all the obstacles. This is just a simple example, the first trial ever that we've tried with our algorithm. And later on, I think this was last year, we tried applying this approach on a real system, on the Jackal robot. Here, the quadrotors here, they are acting as obstacles, and their positions are sensed using some motion capturing system, but we've artificially added some uncertainties to these measurements. And as you can see here, our car is able to safely navigate in this uncertain environment. So, okay, what's next? In fact, we usually don't have as many samples as needed for for efficiently solving the problem that I've shown you. Usually we just have a few samples, or we usually have some learning-based system where we have just a guess about our distributions. So for that purpose, we usually combine the risk-aware control method with the distribution robust optimization-based methods. So what we do here is that we assume that, okay, suppose we have some learning-based system and we've learned the environment, but these learned results are not quite accurate. In that case, what we do is that we say, okay, we have these learned results, but let's assume we have some inaccuracies in the learned distribution. And let's plan for the worst-case distribution within some given ambiguity set. And in all the works that we've performed before, we've always used the Wasserstein ambiguity sets. What it says is that, okay, suppose we have this empirical distribution here, but the actual distribution is the one on the background. So let's say that we have the empirical distribution, and let's build a statistical ball around this learned distribution. And this distribution, the size of this distribution, of course, is a hyperparameter. It determines the robustness of our controller. And then we will choose the worst case distribution from this statistical ball, from this ambiguity set, and we will generate an optimal controller for the worst case distribution. And mathematically, it's written this way. So we have the conditional value at risk, the original conditional value at risk that we had before, but now we add a supremum before. So we are choosing the worst case distribution from the ball that we've defined previously. And here, epsilon is the size, is the radius of this ball, and it will determine the robustness. So here, as I've already told you, we often use the Wasserstein distance between two distributions. It is a distance metric between distributions, and it is very, it has very nice statistical properties. And in fact, other than the statistical properties that it provides, we also have some nice tractability properties. So for example, here we have two cases, two different types of obstacles. So the first one here is a polytopical polyhedral obstacle, and the second one is a circular obstacle. And in both cases, we were able to find tractable solutions to the distributionally robust MPC formulation. So here, actually, in fact, we use two different types of functions. One is we are trying to constrain the penetration distance to the to the obstacle, and the other one is we are trying to constrain the distance to the obstacle. So it seems to be similar, right? But in fact, lots of tractability properties depend on how you define the loss function. So here you can see in all cases we were able to safely avoid the obstacle. So here we don't know the motion, this random motion, anything about this randomness. We only have a few data. And here in this case of the circular obstacle, again, we are able to safely traverse the obstacle. And of course, depending on how we choose the epsilon parameter, our solutions become more robust or more conservative, I would say. All right, so as I've told you, the intuition of using the distribution robust approach is in the situations where we have learning-based systems. So suppose we have this car here, the obstacle here, and the car here is that we want to control is this one, and we want to keep a safe distance from the car that's in front of us. So how do we do that? The easiest approach is to first learn the future motion of the car that's in front of us and then make safe decisions based on these predictions. So the overall algorithm is represented here. So what we do is, this is our environment, or I would say the car that's in front of us. Just generally, it's the environment. So we use Gaussian process regression to learn the dynamics of the car that's in front of us. And after that, we are using uncertainty transform-based approach to propagate the uncertainties through this learned learned dynamics. And we do almost the same for our own robot, for our own car. We are using Gaussian process regression to learn the unmodeled part of our dynamics. And then we combine these two information in a single MPC problem. So to be more precise, now we have this nonlinear dynamics of our own dynamics that has two parts, a known part and an unknown part. And we also have the safety constraint that now depends on an additional state, which represents our environment state. And of course, we don't know how our environment evolves over time, so this F environment is in fact unknown. And also, this unknown dynamics is unknown to us, right? So in our MPC formulation, now we have two unknown parts, the environment state and our own unmodeled part of the dynamics. So as I've told you, we can learn these unknown parts. It's very easy to use Gaussian process regression. But we have a few problems here. One of them is that usually when we are using Gaussian process regression, we use something similar to the nonlinear extended Kalman filter to propagate the states over time, because we need to propagate states in the MPC problem. So one approach that we came up with was using uncertainty transform to avoid the issue of simply linearizing the learned models. And what uncertainty transform says is that with a fixed number of parameters, we should be able to easily approximate the given distribution than to approximate an arbitrary nonlinear function. So the idea is that, okay, suppose we have some predicted distribution. We want to predict the, we have the function here, d function here, and we want to predict the outputs here. So what we can do is we can select some specific points from the input distribution, from the distribution of x, and these points are called sigma points. And we can propagate these points through the nonlinear function, and we can use the sample statistics with some specifically chosen weights to approximate the distribution of the output of these y's. So in the end, we will have the mean and covariance of the outputs. And suppose we call this part of the algorithm UT. Okay, so whatever function d we will have, we will input the moments, the mean and covariance of the inputs, and we will get the output moments. So in our case, what we do first is we collect some data. So this is our own data, right? Our states, our control inputs, and the residual term of the known part of the dynamics. And also we will do the same for the environment. So for the environment, we will collect current states and next states over time. And then we will train a Gaussian process regression that's actually trained in an online fashion. So we keep on collecting new data, we keep on training the Gaussian process regression again, And then we will get the estimate distribution, estimated functions for these unknown parts. And what we do is we use these estimated functions, which are in fact Gaussian processes, to propagate the states of our own states and the environment over time. And what we do is we just simply combine all these things in a simple MPC problem. So here we have the dynamics, and here we have the distribution robust safety constraint. The problem here is that even though we were able to propagate uncertainties over time, we are not able to solve this problem because of the intractability of this risk constraint here. Because if before we were using samples to approximate the conditional valued risk, now we have to also take into account the optimization problem that involves the Wasserstein distance. So in fact, it involves a maximization problem that is in the space of probability distribution. So it's in fact very complex task to do. But luckily, there are lots of approximations in the literature, and one of them was ideal for our purposes. So because we can apply uncertainty transform to also learn the mean and covariance, in this case it's the variance of the loss itself, we are able to find an upper bound on the distribution robust CVAR that will depend only on the mean and variance of the loss, as well as the parameters that we've chosen for the robustness. So in fact, instead of solving this complex bi-level optimization problem, we are able to simply replace it by its upper bound. Of course, it will make our decisions more conservative, but it's simpler and very practical. So now we have tractability, we have a really nice state propagation scheme, and our optimization problem itself involves only simple algebraic equations. Also, we have, of course, because of this upper bound, we have robustness guarantees against learning errors. So here are some results. Suppose we have this car here that has to turn to the left from the intersection, and we have another car coming from the other side of the road. So this first one is the vanilla MPC, where we have no learning and no safety guarantees. The second one is that we have learning, but we truly fully believe this learned results and make decisions based on the mean performance. The third one is the CVAR MPC version, so just risk constraints with no guarantees, with no robustness against learned errors. And the last one is the latest results that we've got with some robustness against learned inaccuracies. And as you can see here we have a collision. We have another collision in the case of mean MPC because we fully believe the learned results. So here we will have a collision. CVAR MPC is not bad, but it struggles a bit to find a feasible solution. So you can see it stops for a bit. And then UTMPC, it actually performs the best here. So let's see again. So as you can see here, this green one is the Gaussian process regression results. And as you can see, this red car, it decides to turn left, suddenly turns left. And because our MPC problem was able to predict such inaccuracies in the learning results, it's able to safely navigate. And here is another example. Same algorithms, a different scenario. As you can see, we have a very evasive car that's next to us, and only UTMPC is able to safely navigate the path without colliding. So once again, here, as you can see here, yeah. Sometimes I hear that my scenarios are not very realistic, but sorry, I don't drive cars, so I don't know how the situation is in reality. But yeah, I think it's good enough to show the performance of our methods. So next is, okay, now we have a single agent, but what about the multi-agent systems? It's actually a very simple extension that will take only 5 minutes of our time, I guess. So now suppose that each of our agents, they have their own dynamics. So here index I, superscript I, it's the index of the agent. So we have NA number of agents that are in the same environment. And each of them have to satisfy some set of constraints, some state constraints and control constraints. So what objectives we have in our scenario, in our case of multi-agent system? So we want to drive each agent to some desired location, to some desired state, in fact. We also want to keep some formation between our agents. And we also want to ensure collision and obstacle avoidance. So for simplicity, for both collision and obstacle avoidance, I keep the same radius r. And also, we simply use the Euclidean distance between the agent and the obstacle or the other agent. So this is a very simplistic scenario, which is, in fact, it works quite nice in reality. So we will be using a distributed fashion of controlling all the agents, because first of all, it will be easier for us to scale it up to lots of agents, right? And also, we want to have this collaborative fashion where each agent will convey its information to the neighboring agents and see how this information can be used. So, okay, what we do is that we have a few assumptions. The first assumption is that all our subsystems are independent. So each agent can make its own decision. Also, any information that an agent needs can be conveyed through a communication, or it can also perform some predictions to find any information that it needs for making decisions. So how we define our stage-wise cost function for our MPC problem? We have the tracking part. Because we want our agent to track some given reference trajectory or to reach some point or some state. Then we also have the formation part of the cost. Also, we have the control energy. We also want to minimize the control energy that's being used. But please be patient here, because we also need the states of the neighboring agents, because our decision depends on our neighboring agents' decisions, right? So what we need here, so this minus I here, it means the states of all the agents except of us. So what we do here is that we follow a very simple idea. So each of our agents will solve an MPC problem, will try to minimize the given cost function, so that the controls also satisfy the dynamics, also satisfy the collision and obstacle avoidance constraints. But as I said, we need the states of the neighboring agents. For that, we follow a simple idea. We just convey our MPC predictions to our neighboring agents. So for each of our neighboring agents, they will use our predictions in their MPC problems. So in that case, the problem is that we might have some prediction uncertainties, because we not always follow the MPC predictions that we have in the previous time steps, because we have an uncertain environment, we have a dynamical environment. We might also have some sensing or communication noise. We might have some model uncertainties, etc. Oh, actually, there are some repetitions here. So what we say here is that, okay, suppose the predictions of our neighboring agents are uncertain. So in fact, they follow some distribution. Also, we have some state estimation uncertainties. So our own states, they follow some distribution. And on top of that, we might also have some perception uncertainties. So the static obstacles that we observe in the environment might be uncertain. So they also follow some distribution. So the easiest thing to do is that, okay, let's just replace all the constraints, all the collision and obstacle avoidance constraints, with the respective conditional valued risk constraints. That's a very easy transition, because so basically the loss function that we have for this constraint is 2r minus the distance. So basically that's what we have here. And because we have the distributions of each of these uncertainties, we are able to formulate an MPC problem with these risk constraints. So in reality, we might not have these distributions, but we may have some samples. For example, in a single decision-making period, we might be able to observe, we might be able to get several observations. In that case, we will have, for example, 10 observations in 0.1 seconds. So what we do in this case, each of the agents convey their predictions to their neighboring agents, and each agent solves corresponding MPC problem with the risk constraints. So the overall algorithm is shown here. So in fact, this for loop here is performed in parallel for each agent. So each of the agents solve their MPC problem. They apply the first control input, and then they transmit their MPC predictions to the neighboring agents, while the neighboring agents collect nj number of samples of these predictions. And then each of them solve their corresponding CVAR MPC problems. So here you can see, oh, it's very dark here, but you can see an example where we have two crazy fly drones. I'm not sure if you are familiar with the crazy fly drones. They are very small drones, usually used in academics. It's just a very simplistic scenario, and in fact we've tried this scenario in real life, but I wasn't able to film the results in the last minute, so sorry for showing only the simulation results. But here we have these two quadrotors, two crazy fly drones flying. Here we have a vanilla MPC problem where we are just using the predictions as they are. So you can see here, because we have some prediction uncertainties, let's see, they should collide with each other, in fact. So let's see if they collide. So here you can see these two drones. They are trying to avoid each other, but in the end they are colliding because we have some uncertainties in the predictions. And this is the second scenario here, where we have the risk-aware MPC solved in real time. So each of the drones, they transmit their predictions to the neighboring agents, and these agents are using this information with some uncertainty. They don't help, and you can see even the predictions that they are quite safe here. So in fact, this was only the results for the risk-aware MPC, and these are really preliminary results that we've just performed recently, very recently. And let's go to the next slide. Yeah. So to conclude, we've come up with this idea of using risk measures to design a risk-aware control algorithm for both single agents and multi-agent systems. And we were able to also account for learning inaccuracies in these predictions by using some ideas from the distribution robust optimization. And though we have some preliminary results for the multi-agent systems, our next step would be to also incorporate some learning inaccuracies or prediction inaccuracies, and also add this distribution robustness on top of these predictions. So our next step, of course, would be to find some nice scenarios. If you have any ideas on how to use these algorithms, or how to come up with some nice scenarios, we are more than welcome. You are more than welcome, of course, to tell us. So that's it for today. Thank you very much. And if you have any questions, you can ask them now, or you can also contact me via email. Sure. This one, yeah. So I made them meet each other. So they are kind of it's a different, it's a difficult scenario. They have to meet each other and then try to avoid each other. So this one, it uses let me go back. This one uses the naive, just a simple, simple constraint like this one. While the second scenario, it uses the risk constraints. So they have to meet each other. They are on the same level. Yeah, and they have to avoid each other. Yes?
In the simulation and in the experiment, your C bar, your risk measure is changing in real time, right?
Yes.
And are these risks, that uncertainties that you inject as Gaussian, or do they have tail distribution?
So in my case, they are Gaussian. But when we are doing real-world experiments, we do not inject any artificial noise. We are using samples from the actual drones. Because, like for example, in our case, we are using the onboard flow deck sensor, optical flow sensors for state estimation. And these state estimation decks are usually quite inaccurate. So, for example, our control problem is being solved in 10 Hertz frequency, while we are able to sense in 100 Hertz frequency. So we are able to get 10 samples in each control iteration.
All right. Thank you for giving me this opportunity to present this work. Dr. Vugaris was my postdoc advisor when I was working at the UNR. He was supposed to come here, but he couldn't, so I am presenting this work. Now I'm at Tennessee Tech as an assistant professor. I started about 2 years ago. So the talk that I'm going to give is on the use of reinforcement learning for autonomous vehicle to generate adversarial image perturbation against the object detector of the cars and aerial vehicle. So a lot of people already know that this computer vision that use a deep neural network, they are very popular and widely used, maybe more than a decade now. And about 10 years ago, people found that the deep neural network can be very susceptible to small, tiny perturbation. From our eyes, we can see the panda on the left, and the panda with very slight perturbation. It looks same to us, but for the deep neural network, sometimes it can misclassify. So an idea behind all this work is maybe using this, we can find the weakness of machine learning tools.
We can hear you.
Oh, something happened. Let me show you again. So I believe that you guys can still see it and hear me.
Yes,
thank you for
we can.
patience. Good. So similar to the previous example, I generated some perturbation. You can see some marks at the start side. Using this, you can move away this object detection bounding box to arbitrary location, like this. And I'm attacking using this. So the vertical perturbation is very simple, looking like this. So I have object detection here, that will give us a target bounding box, and there's a very simple tracking controller. Basically, you want to try to keep this bounding box as centered and with the appropriate size so that you can keep the distance and then keep the target at the center. And so that controller generate velocity command, and then and the adversarial perturbation use this camera images, and there are certain reward according to the adversarial objective. That could be losing tractions, target tracking, or it can aim to crash some vehicle. So I was not the only one looking into this type of research or this type of the topic. So there were existing methods. And this is one of the methods which was before my work. And as you can see, the adversarial patch is very colorful. Unlike the very first panda misclassification example or mine, that's one downside of this existing method. Another thing is that actually they generate this adversarial patch using multiple time step offline optimization. So that means it cannot generate real-time attack. So I made the use of reinforcement learning, and also I added this binary decision maker to make the attack more stealthy. Basically, it works as when it has another device that determines whether they are proficient or effective in generating the attack or not. So I have added this binary decision maker in addition to reinforcement learning. So implementation of this one takes several ROS nodes or the programs. So I've been using AirSim or Kala or modified Kala as an environment, and also I use a very simple small indoor UAV to demonstrate all this work. And so left-hand side is the controller and object detector, and then right-hand side is the real-time image attack generation parts. So all of them are running simultaneously, exchanging the data over ROS network. And this is a video that shows. This is normal operation. Normal operation is very simple. This small drone goes to the target. That is simply car. And then I'm using all this method that I mentioned to you. I can add the perturbation. In this example, the perturbation is added at the, you can see it, not see it easily, but it is added here. So that's why you see the cars right there. And then another nice thing about my approach is that I can use different levers so that I can move it to the left or to the right, depending on the adversary's objective. And because all this attack is generated by using the full model knowledge, so you can actually do this training using just 10 minutes. So there was no pre-train in this experiment. Maybe training does not make sense because we already know all the parameters of this YOLO model. But it has some adaptation, that's why it takes some time. But spending just 10 minutes, you can make it crash. You can apply the same approaches to the color environment. It's not very different. It is actually the same, but just with different environment. Well, how can I? Oh, there's no. In normal operation, it works like this. I am looking for way to skip this. A lot of part of the video, but let us see it. I think it won't take too long. I guess this is normal operation. And when it works. The baseline method is, in this case, it doesn't turn it on and off using this binary switches. And somehow the tag is less effective, but if I switch on that binary decision maker, and it actually kind of exploits so that it initiate attack when it is more capable. So this is baseline, and you can see that sometimes that works slightly, but it is not strong enough to fail this objective or mission. And if you can patiently wait for maybe 1 minute, I think you will see the proposed method. Come on, when it's going to. The proposed method final. It is much more effective. Okay. Because my talk is too short, so I wanted to also introduce some of the all that work that I do with the simulation environment. Let me go through them very quickly. So all the simulations are already by use, even starting 2 or 3 years ago, Tesla or all the other autonomous vehicle companies. And then nowadays, I think that a lot of four-leg robots are trained in this simulation environment, and there are a lot of humanoid robots that are trained with all this simulation environment. And then I started working with this since 2023, and then we are trying to get better visual quality by moving from Unreal 4 to Unreal 5, and then more toward to real hardware from just simulation. And you can do simple vision-based landing using this kind of simulation environment or part of the same YOLO network. Unreal 5 has a better computer graphics, as you can see here. And then this is one of the use case of this simulation environment. So the idea is I trained this helipad detection using the open source, someone curated helipad from Google Maps, and I think 5,000 about helipad images. I trained this object using those images, and then I expected that maybe depending on the lighting condition, maybe this pre-trained model can be better or worse. That's my thought, because the data is actually from the satellite imagery, and then the resolution is also different. So it can have the different performance, and the idea is a data augmentation. So I pre-trained it, but if I rescale the images and also change the brightness, that will augment more data. And also I can have feedback in this optimization. Basically, it chooses what kind of data can be useful to improve the performance. So using this, we were able to improve the landing success rate from the 50% to 70%. It is not perfect because we have several random initialization and all of that, but this is to show you that this kind of data augmentation can be useful, and this is a good use example where the simulation is useful. All right, and another use case that I had was switching between two controller. So you can see that here with low gain in this tracking, you don't lose the track of this object much, but with slightly more gain, and then as you can see that it can introduce some camera blur. So that's why it loses more, and with higher gain, yeah, it will oscillate, and it loses the tracking more. So there was a motivation. So what you can do is, you know that in robust control, they use optimization for system optimization, right? You can make it more robust to noise, you can make it more robust to disturbance for the better performance. So by this different weight in your robust control, you can make up some controller, two controller. One is useful for dealing with the uncertainty in the object detectors. And we use the simplest uncertainty estimation method, that is a 5 ensemble. We train the 5 different YOLO model with random subset selections. So we have 5 different models, and then they will be in consensus for more repeated data, because the repeated data will be likely to be included in all these five subsets. So that's the idea how this uncertainty estimation works. As you can see, as dust level increase, this uncertainty is greater. How you can see this thin line away from this thick bounding box represent the variance of the coincidence, the bounding box. So as you can see, as I increase the dust level, the uncertainty increase. And then what I did was I have the two controllers. One of them is for the performance, the other one is for the robustness to this sensor noise. And I use threshold to switch from performance-oriented controller to robust-oriented controller. Using this, you can have a better terminal error. So this demonstrates that this can be one of I use the uncertainty of the object detector, and then switching, given this uncertainty, can be a way to improve the performance. So very briefly, I also studied as I moved to Tennessee Tech, and now I am using my student to develop VTOL. There are many hobbyists who develop something like this. But a good thing about this one is it has a 3 kilogram payload, and so that I can mount something like NVIDIA Jetson Nano. That is much more powerful than other small GPU or NPU mobile computers. So that's the plan, and also the ROS that I use. Now I'm switching to NVIDIA is a ROS because they are better maintained. So and it has a GPU acceleration. So I'm borrowing all this nice collection, and that is maintained by NVIDIA's. You can do something like this very easily using the open source. And I plan to use it with some hardware in loop simulation environment. And we are also making real hardware in addition to this hardware in the loop simulation. It is nothing for someone who already studied on this, but it was quite a journey for us to have this first practical take-home. Okay, now I'm at Tennessee Tech, but I used to work with Dr. Burgers. That's why I'm presenting this work here. Thank you very much. This is all I prepared for today.
It's my pleasure and honor to present my joint work with Professor Naira Hawakilia on uncertainty compensation in safety and efficient control of uncertain system. A delivery drone, a self-driving car, or air taxi, and autonomous space aircraft are safety critical. And the failures of these systems can cause significant economic losses and serious risks to human lives. And we may also know that actually many real-world systems are subjected to uncertainty. Okay, in the dynamics, this could be denoted by additional term besides the nominal term. Okay, take a delivery drone, for example. The uncertainties could represent the unknown parameter induced by unknown payload, unmodeled dynamics due to the complex aerodynamics, external disturbances, for example, due to wind gust, as well as physical failures. Okay. And the model uncertainties actually can exacerbate the trade-off between safety and efficiency or performance. Okay, so for guaranteeing safety, okay, one way is to be very conservative. For example, fly slowly and try to stay very far away from the obstacles. However, this is not what we want. We wanted to fly faster and also close to the obstacle for the sake of efficiency. So the focus of this talk is to investigate how we can ensure safety, which is basically enforcing state constraints without much sacrifice of efficiency. And for the specific work, I'm going to first present how we leverage uncertainty compensation to achieve efficient constraint control. And next, I'm also going to present how we can use uncertainty compensation for safe and robust reinforcement learning. Okay, to enforce constraints or safety, there are actually already a few control paradigms for this. For example, model predictive control, reference governor, barrier Lyapunov function, or control barrier function. Okay, so let me see whether I can use a pointer. Okay. Pointer. Okay, and in the presence of uncertainty, we have actually different robust and adaptive version of these constraint control methods. For example, robust adaptive MPC, robust RG, robust adaptive CPF, so on and so forth. Now let's take a look at the existing robust adaptive constraint control approaches. Okay, so existing robust constraint control approaches, for example, robust MPC or CBF, they typically consider bounded disturbances and can lead to conservative performance due to considering the worst case scenario. Okay. And adaptive constraint control approaches, for example, adaptive MPC or adaptive CBF, they can improve the performance and reduce the conservatism with parameter estimation. However, they are generally limited to parametric uncertainties, and their performance depends on the accuracy of the estimated parameters. So we are interested in see whether we can achieve more efficient constraint control using uncertainty compensation. So the idea is as follows. Suppose here we have an uncertain plant. We can design an uncertainty compensation controller to actively compensate for the uncertainties so that our uncertain plant behaves like a nominal plant with pre-computable bounds. And then we just needed to design a constraint enforcing controller for the nominal plant with tightened constraints. Okay. So the idea actually is quite simple, but the challenge is how we can design the uncertainty compensation controller and derive meaningful transient performance bounds. Okay. So before we move to the solution, let's just take a look at the basic idea of uncertainty compensation. So here we have an uncertain plant, okay, with this nonlinear plant with this uncertainty dtx. Okay, if we can use a design uncertainty estimator to estimate this uncertainty as d hat t, then we can design an uncertainty compensation control law to cancel the uncertainty based on this estimate. Okay, and if this estimate is accurate, then we can cancel the effect of the uncertainty to achieve the nominal performance. Okay, and typically uncertainty compensation controller works as a add-on module. Typically, it augments a baseline controller, which is designed to achieve the desired closed-loop performance in the absence of uncertainty. And then this uncertainty compensation controller is designed to cancel the uncertainty. Okay. So that is the basic idea. Actually, this idea of uncertainty compensation has been explored in different control paradigms, which mainly include model reference adaptive control, disturbance observer-based control, which further includes an unknown input observer-based control, and active disturbance rejection control. And finally, we have L1 adaptive control. In this talk, we mainly leverage L1 adaptive control as a tool, primarily because of its unique advantages. In particular, it can handle a broad class of uncertainties while allowing us to derive transient performance guarantees. Okay, so which we will look into this in detail later. Okay. So along the uncertainty compensation based constraint control idea, so recently we have developed this integrated L1 adaptive control and reference governor control architecture. So here we consider a linear nominal system with matched nonlinear uncertainties. Okay, so this can nonlinear uncertainty DTX can represent a broad class of uncertainty like unknown parameter and model dynamics disturbances. And the system is subject to both state and input constraints. Okay, and we are interested in reference tracking problem. So our idea actually consists of 4 steps. First, we design our L1 adaptive controller, okay, here, to cancel the uncertainties, okay. And then we derive the transient performance bounds of the closed-loop adaptive system with respect to a nominal uncertainty-free system, okay. And then we use these transient performance bounds to tighten our original state and input constraints. And finally, we just needed to design a reference governor for the nominal system with the tightened constraints, which will guarantee the constraints can be satisfied for the original uncertain systems. Okay. So now let's look into some details of each step. So here's the control architecture of L1 adaptive controller. Here we have a state predictor and adaptive law that works together to estimate the uncertainty. And then we use a low-pass filtered control law to cancel this uncertainty. Okay. And with some new technique based on scaling, we are able to design actually separate bounds for each state and adaptive input channel, basically with respect to the response of a nominal uncertainty-free system. Okay. And these bounds actually depends on the low-pass filter, in particular the bandwidth of the low-pass filter and the adaptive sample time. Okay. And we can also ensure that these bounds, the state bounds, can be arbitrarily small by increasing the bandwidth of the filter and reducing the adaptive sample time. Okay. So another element of our proposed control architecture is a reference governor. Okay. So reference governor is an add-on scheme to enforce constraints by modifying reference commands online. So the idea is that we already have a baseline controller that can give us desired closed-loop response in the presence of small or slowly changing reference signal. Okay, and then but without considering these state and input constraints. Then we can add this reference governor to modify this reference as needed to ensure that both the state and the input constraints can be satisfied. Okay. So the advantages of a reference governor compared to alternative scheme like MPC, main MPC, is that it can preserve existing controller. It can also maintain the stability and robustness guarantees provided by the baseline controller. And it is also computationally efficient compared to MPC. For example, for a scalar reference governor, we just needed to optimize one scalar variable at each time step, okay, which can be efficiently solved. So here we show our control architecture, okay, including L1 W controller and the reference governor, and we are able to prove that under certain conditions, okay, so we can ensure both the state and the input constraints are satisfied, and also our actual state is bounded from nominal state. Okay. And in a follow-up work, we extend the preceding idea to the MPC setting. Okay. So actually, as you can see, the control structure is quite similar. Still, we have an L1 adaptive controller that compensates for the uncertainty, and we have an MPC designed for the nominal system with the tightened constraints. However, we have an additional component, which is a robust baseline controller. Actually, this robust baseline controller is introduced to handle the unmatched effects, the unmatched uncertainties, basically to mitigate the effect of unmatched uncertainties. So, you know, in the previous setting, okay, so we can go back a little bit. In the previous setting, we only consider matched uncertainty that basically are injected into your system through the same channel as their inputs, and therefore can be and their effects can be completely cancelled. However, in this setting, in addition to have these matched uncertainties, we also have these unmatched disturbances. Okay, and in this work, we basically use this robust baseline controller designed using LMIs to mitigate the effect of unmatched uncertainties, WT. And compared to existing approaches, our uncertainty compensation-based MPC can handle a broader class of uncertainties compared to existing adaptive MPC schemes. Okay. And we are also able to reduce conservatism compared to existing robust MPC due to the active uncertainty compensation within our controller. Okay. So we applied our UCMPC to an asteroid landing problem. We use the asteroid 433 Eros. Okay. And we consider uncertainties, including this uncertain gravitational force and also the linearization error. Because the actual dynamics are nonlinear, but our MPC is a linear MPC. We use a linearized model for the MPC design and also the adaptive controller design and the robust baseline controller design. Okay, and the landing actually consists of two phases. The first phase is to fly toward a point above the landing point while avoiding the colliding into the asteroid. And the second phase is to land. Okay. Through the simulation and the plots, we can see that actually our UCMPC recovers the nominal trajectory, which is actually achieved without incorporation of any uncertainties. Okay. And we are also able to enforce constraints for both phases. Actually, in the first phase, we use a rotating hyperplane to ensure that the asteroid does not collide into the ellipsoid that circles the asteroid. And in the landing phase, we use a pyramid shape to define the constraints. Yeah, so just now we mentioned that actually a few different constraint control schemes, including MPC reference governor and control barrier function or CBF. And next, we will show that actually we can also incorporate uncertainty estimation into CBF to develop a more efficient CBF controller and uncertainties. Okay. So as you may know, CBF is a popular tool nowadays for synthesizing safe controllers for nonlinear systems. And it often works as a safety filter that modifies the control commands from a nominal controller minimally to enforce safety constraints. Okay. And it's typically the control signal is determined by solving a QP, which is a quadratic programming problem subject to derivative condition. And when we apply this CBF to an uncertain system, actually we will have a show. Consider here we have uncertainty DTX. Okay, and suppose we are giving a CBF function h. Okay, and when we look at the derivative condition for the uncertain system, we will immediately notice that the derivative condition actually depends on the uncertainty d, which is not accessible to us. As a result, this condition is not implementable. Okay. However, if we can estimate the uncertainty, suppose we can estimate this uncertainty as a d hat t, while also providing an estimation error bound, let's say gamma, okay, and then we can derive a sufficient condition, okay, sufficient condition that depends on only on this estimated uncertainty d hat as well as the estimation error bound. Okay, and obviously this condition is implementable. Okay, because we can have access to this d hat and gamma. So that is the main idea behind this the uncertainty estimation based CBF. Okay. And some details about the uncertainty estimator. We adopt a piecewise constant estimation law, actually, which is often used as within L1 adaptive controller. And we are able to establish an estimation error bound. Okay, and the error bound depends on the properties of the nonlinearity. And we are also able to show that after a single sampling interval, the estimation error can be made arbitrarily small because this we can make this gamma t goes to 0, okay, by reducing this sample time t. And of course, in practice, the size of t is limited by computational hardware and measurement noise. Okay. So we applied our approach to this adaptive cruise control problem. We consider unknown aerodynamic drag terms and external forces as the uncertainties. And we select this CBF to achieve a desired head weight time. And we use a control Lyapunov function to construct the baseline controller. But actually, this baseline controller will try to achieve the desired speed for the ego vehicle. And we compared 4 different methods for handling the uncertainty. Okay, in the first case, we use the true uncertainty. This represents the ideal performance we can achieve because in practice we can never have access to this true uncertainty. Okay, and our approach using this uncertainty estimation as well as estimation error bound. And the third way, we ignore the uncertainty. Okay, the final way is existing robust approach that consider the worst case bound for the uncertainties. Okay, so it's a pure robust approach. And we can, and here this LED light indicate whether the CBF function is non-negative or not. Okay, non-negative means the system is safe. Okay. And from the simulation results, we can see that actually ignoring uncertainty leads to uncertainty estimation-based controller actually from these left 2 plots, we can see that our uncertainty estimation-based controller almost recovered the ideal performance, okay, which is achieved using the true uncertainty. Okay, so how many time I have? Okay, so I have 4 minutes. Am I correct?
Yes, you have 4 minutes left.
Oh, okay, 4 minutes, yeah. So then let me quickly go through how we use uncertainty compensation in safe and robust reinforcement learning. Okay, so previously we mentioned that we designed this uncertainty-based CBF. Actually, here we just use this uncertainty-based CBF to ensure the safety of a reinforcement learning agent. Okay, so we use in particular we use a disturbance observer. Okay, and our framework relies on uncertainty estimator, so no need for model learning. Okay, well, I forgot to mention that we consider the dynamics are partially known. Okay, partially known, and we have this D as the uncertainty. Okay, and our framework can work with any model-free RL algorithm. So we test our framework on this 2D quadrilateral example, and the uncertainties from rotation friction motors and air resistance. And we use the soft actor critic as our algorithm. We compare our approach with a state-of-the-art method based on Gaussian process regression and CBF. Okay. And we can see that actually our approach achieved a much higher sample efficiency. This is primarily due to the fact that actually we can provide the estimate starting from the beginning, while the estimation accuracy of the GP-based method is quite low at the beginning. And we also compared the safety violation rate as well as the computational time and their tracking performance. And overall, we can see that our method maintains a lower constrained violation rate and also significantly reduced computational cost and also better tracking performance. So in the previous work that I just mentioned, we are trying to ensure safety during the exploration of the training stage. Okay. You know, another problem of reinforcement learning is a policy trained in a nominal environment could fail in the presence of dynamics change. This dynamics change could be due to similar to real gap when we train the policy in a simulator and deploy it in the real world, or environmental perturbations when we train the policy in the real world. Okay. So existing approaches can be, for handling this problem, can be classified into robust training and online adaptation methods. Okay, so the robust training methods, including domain randomization, they involve extensive modifications to the simulated training environment, and they also potentially lead to conservative performance due to reliance on a fixed policy. Okay. On the other hand, online adaptation, they can reduce the conservatism of robust training, but they are purely data-driven, and they may not react fast enough to handle sudden dynamics change without failures. So our approach is to fast adapt a policy using uncertainty compensation. Okay, so within our framework, we can train our policy in a nominal environment. Okay, and then when we deploy it, we add adaptive controller to estimate and compensate for the uncertainties, okay, or for the dynamics change, okay. In order to make our perturbed environment plus the adaptive controller closer to the nominal environment. Okay. And since our policy is trained in the nominal environment, and most likely it will work when our perturbed environment is close to the nominal environment. And besides validating our method in simulations, we also tested on a hardware pending board system. Okay, so the task is to swing these two links, okay, from the downward position to the upward position and balanced there. And we train 3 policies in simulation based on Pilco, soft active critic, and soft active critic plus domain randomization. And then we evaluated the performance of the policies and different perturbations, including reducing the control effectiveness to mimic the actuator failure, and added meshes and added disturbances with a rubber band and their combination. And we can see that actually from this table, we can see that the uncertainty compensate. Oh, here we use the L1 adaptive controller to estimate and compensate the uncertainty. So we can see that this uncertainty compensation significantly improved the success rate. So next, let's just look at some test cases. Okay. The first case is a nominal case. So all the policies with or without compensation succeeded. So this is the easiest scenario. Okay. And in the second case, we reduced the control effectiveness and also added some math. And we can see that actually without compensation, only the domain randomization trained policy succeed. Oh, let's see it again. Oh, actually, without compensation, all policies it fails. Okay, and with compensation, 2 policies succeeded. And in the third case, we add a rubber band to induce disturbances to the system. You can see that with compensation, all the policies succeeded. And without compensation, only the domain randomization trained policies succeeded. Okay. To summarize, I have presented. I have shown how we can use uncertainty as compensation to develop efficient, safe, or constrained control schemes for uncertain systems. In particular, I show how we can integrate uncertainty compensation with reference governor, NPC, and CBF. And I also show how we can use uncertainty compensation to ensure the safety of RL agent during the training stage, as well as how we can fast adapt the RL policy using uncertainty compensation. And through my presentation, we can see that actually the transient performance bounds of the uncertainty compensation controller or the estimation error bounds are the key for this to develop this efficient, safe, and constrained control. And in most cases, we adopt the L1 adaptive control. Okay. Finally, I would like to thank my collaborators and my sponsors. This concludes my talk. I'm happy to take any question.
Thank you, Pen. Let's thank the speaker once again. Is there anyone from the audience that would like to ask a question? Okay, if no, Pen, actually, I have one question. Can you hear me?
Yes, go ahead.
In your reference governor, you mentioned that it is less conservative than, for example, a robust controller. Why is that so?
Because, okay, so let me reshare my screen. Because in robust approach, we typically consider the worst case bound on the uncertainty, and then we are just trying to be robust against. We try to ensure this robust, constrained satisfaction. In contrast, in our approach, actually, we have some uncertainty compensation embedded in our control, which means that we will actively cancel the effect of the uncertainty. Actually, this simulation example can well illustrate this. So here we compare, or we consider F16 longitudinal dynamics control problem. We compare our L1RG with a robust RG approach. Okay, so this is a robust approach. We can see that in terms of constrained enforcement, actually both RG and our L1RG successfully enforce the constraints. But if you look at the tracking performance, okay, so this green line denotes the reference. So, and this red line denotes our approach, okay? And this blue line denotes the robust approach. Okay, we get a much better tracking performance. Because we cancel the uncertainty, and then we just needed to handle the remaining uncertainty. Okay, so and if you cancel most of the uncertainty, your remaining uncertainty is just a little bit, and you should be able to get a better tracking performance and also less conservatism in enforcing the constraints.
Okay, thank you very much. Thank you, Pan.
I'm glad to be able to present our recent work for you today on robust trajectory generation and control for quad rotor motion planning with field of view control barrier certification. This work was done by my student Lishuo Pan and our collaborators Mattia Catalani and Professor Lorenzo Sabatini. Our motivation for this work is twofold. It's motivated by our desired applications and what we see as limitations in existing algorithms. First, we're motivated by specific applications of multi-robot systems. Multi-robot coordination is prone to failure when there are losses in communication and uncertainty in estimation of the location of team members. Thus, we wanted to develop a communication-free approach to true coordination. Next, using onboard sensors allows us to build a distributed approach and is robust to communication loss. However, using onboard sensors to localize your teammates is often limited by field of view constraints. Thus, we want a distributed approach that can keep the neighbors inside that limited field of view. In this image on the left, the group of Giuseppe Loiano and Lorenzo Sabatini worked to preserve graph topology with limited field of view using control barrier functions. We also want the visual tracking to be robust, in that we should be able to tolerate temporary visual tracking losses and regain that visual tracking quickly. We are interested in control barrier functions because of their safety guarantees, but as it is a reactive safety filter, it leads to an aggressive controller, which can cause infeasibility and failure. In the center image, we can see control barrier functions in a discrete formulation on the left side, which ends up being quite aggressive and short-sighted. On the right side of that same image, you can see what it looks like when combining model predictive control with control barrier functions. And this is work from Kushal Srinath's lab. Thus, we combine control barrier functions with trajectory planning and do so in a continuous time formulation in order to improve the task success rate. By using piecewise splines, we can then generate a continuous time trajectory and a controller concurrently. Piecewise splines, or Bezier curves, have been popular for some time in trajectory planning, especially in the work in my lab here on the right, since we can ensure smoothness to an arbitrary degree by changing the number of control points. Let's do a very brief overview of control barrier functions. Control barrier functions ensure safety by constraining the control input to the system so that the system stays within a predefined safe set. Considering that we have multiple agents in a shared space, these boundaries can be approached quite quickly, which is something, of course, we want to avoid. In our formulation, we assume the system is a double integrator, so we require the usage of high-order control barrier functions in order to satisfy the constraints. In our work, the relative degree of our control barrier function with respect to dynamics is of order 2. The higher order control barrier function constraint is in the form of the equation above. Further, we adopt high order control Lyapunov barrier function formulation for our HOCBF, which uses an extended kappa function as the alpha function. By employing this formulation, the system converges toward the safe set when outside, in addition to being forward invariant within the safe set. This property is desired for robust controller design. Our task objective is to develop a real-time, communication-free, distributed algorithm for navigation that is certified by control barrier functions that model and control the onboard sensing behavior to keep neighbors in the limited field of view for position estimation. We propose the MPC CBF, or Model Predictive Control, control barrier function framework, which generates a continuous time trajectory and controller concurrently using piecewise splines, and that is certified by control barrier functions. Our proposed algorithm is robust in that it tolerates temporary constraint violations and can drive the system back to the safe set. That is, it allows the robot to regain visual contact with its neighbors after temporary tracking loss. This is essential when uncertainty is present or the problem is temporarily infeasible. In the multi-robot scenarios, this temporary loss of tracking is inevitable. To formalize our problem, consider N robots in a communication-denied workspace W. We denote RRI as the set of points representing robot I, or its volume, at position Ri in R3. Robots are required to navigate to their respective goals. In other words, they are not moving as a group to one location, but each of them have independent goals they need to satisfy. The constraints are that the robots cannot share information with each other. There is no explicit communication. However, they can estimate the position of the other robots using an onboard camera when they are within the camera field of view. Our controller outputs a continuous time trajectory and control policy concurrently in a receding horizon fashion to navigate toward individual goal positions while maintaining visual contact and collision avoidance with other robots. We assume a double integrator model where a robot's state is its position, yaw, and their first order derivatives. And we model the sensing region as a truncated spherical sector, which you can see here has a minimum safety distance and a maximum detection distance between which a neighbor can be detected safely. Here is an overview of the system control loop. As this is distributed, each robot, or quadrotor in this case, is running its own loop, and notice that there's no input coming in from any other robots. The quadrotor uses a particle filter to estimate the position of neighbors and uses this information in the planning. Specifically, our MPC CBF module generates certified trajectory and control, which control the quadrotor to updated states. In this talk, I will focus on the MPC CBF and the HOCBF design. We consider safety as obeying three constraints: safety distance, sensing range, and field of view constraints. There is a minimum distance between robots in order to prevent interference and collision, which we call DS. And you can see that on the sector on the left here. There is a maximum distance beyond which a robot cannot effectively estimate the position of a neighbor, the maximum sensing region, which we call RS, and that's here. And there are horizontal and vertical angles that represent the camera's field of view, beta H and beta V. In our experiments, we have worked with both a limited field of view and also a full 2π for the horizontal angular range. Since we are dealing with quadrotors, we are especially interested in smooth trajectories, so we use a Bezier curve as our trajectory plan and its second order derivative as the controller. Thus, we get both trajectory and control policy concurrently. We choose Bezier curves specifically because we know that a Bezier curve lies completely in the convex hull of its control points, so we have a good idea of where the robot will be while executing. It is smooth to an arbitrary order of derivatives, and its curves and its derivatives can be represented by a linear combination of control points. The derivatives are computed as a closed form of the control points, which are the decision variables in our optimization problem. Here is a general form of trajectory planning certified with control barrier functions. Notice that constraint 12E here introduces an infinite number of constraints for all time t. And this, of course, makes the problem intractable. To address that intractable optimization, we propose a sampling-based optimization framework. Instead of requiring control barrier functions at all times, we impose the HOCBF constraint only at timestamps sampled at fixed intervals over the horizon. Here, we have the robot at the bottom heading to its goal, the bottom red dot, while operating close to their neighbor. You can see the predicted field of view shown as blue triangles during the planned trajectory. So you can see the robot faces to the left and then slowly turns toward the right. But you can also see that the robot is trying to keep the current position of the other robot in the field of view, since it doesn't have any knowledge of the other robot's trajectory. As samples increase, then we can approach the HOCBF constraints. Since our optimization scheme acts similarly to an MPC with continuous time control inputs, we name our algorithm Model Predictive Control with Control Barrier Functions, or, as I've mentioned, MPC-CBF for short. Now we walk through all the constraints in the proposed optimization framework. First, the HOCBF constraints in equation 13 are nonlinear, as the predicted state depends on the decision variables, and ACBF and BCBF are nonlinear with respect to the states. We propose an SQP to solve it efficiently. We introduce slack variables to relax the constraint. As we're in a complex environment, it is not manageable to satisfy all field of view constraints, especially if you have many robots. Plus, distant robots don't pose immediate danger of collision. For collision avoidance between robots, a control barrier function constraint can only avoid collision within the current estimated position of neighbors, as the robot cannot know a neighbor's future position. Thus, it cannot provide a guarantee of being collision-free in the horizon. To account for this, we use a separating hyperplane, which creates a safety corridor in which the robot plans its path. This approach still cannot guarantee a collision-free trajectory, as one, the separating hyperplane might be mismatched between robot A and robot B, and robot B and robot A. And two, the estimation uncertainty. However, it provides a more conservative trajectory plan that does better at avoiding collisions. Bezier curves allow us to obey continuity constraints and stay within the physical limits of the robots. Our optimization problem has three objective functions. First, the goal-reaching cross tries to minimize the distance between the last kappa predicted position and goal. Next, we minimize the control effort. And finally, the priority cost minimizes the slack variables of nearby neighbors first. And nearby here is defined in the belief space. We compute the distance as the distance between the ego robot to the neighbor's 95% estimation uncertainty ellipsoid, which contains the neighbor's position with 95% probability. If one of the neighbors is not being tracked for long, its estimation uncertainty will grow and thus reduces distance to the ego robot. This leads to tracking priority. And you'll see in the video that I'll show later how those ellipsoids actually grow when robots are not within each other's field of view. We solve the optimization using sequential quadratic programming. The main idea is to solve multiple iterations of quadratic programs in one loop and treat the predicted state as constant from the last iteration solution. As we discussed before, the constraint 21E is nonlinear. This one right here. As the predicted state depends on the decision variables, and ACBF and BCBF are nonlinear with respect to the states. We use the solution from the last QP iteration and plug into constraint 21E. For the first iteration, we solve the QP without constraining the predicted state in the horizon. Here is an example of 5 robots flying to antipodal points in a circle. In all of the experiments I will show here, both simulation and physical robot experiments, we fix the height of the robots. We test with different ranges of beta h, or the horizontal camera field of view, to demonstrate the properties of our algorithm. I'm going to zoom in real quick here, just to show you some things that are hard to see otherwise. The 95% confidence ellipsoids of estimation uncertainty are represented as ovals, and the source of those estimations is indicated by the colors. So, for example, the yellow robot on the right here doesn't have the green robot, which is up here, and the magenta robot, which is down here, in its field of view. You can see the cone here. So this is the cone of its field of view. So their estimates have a large uncertainty, and you can see that the estimate is from the yellow robot, and that's why the ellipse is yellow. The predicted output, the position and yaw, is depicted as blue curves and fields of view. So here are the blue curves, for example, and these cones depict the predicted field of view. The path of each robot is shown in a solid line in that robot's color. Now note that the robot colored in the green, so this one up here on top, loses visual contact with neighbors at the end of its trajectory here. So it's facing a completely different direction. And thus, it changes its positions and heading, which we'll see in the next panel, to regain and maintain detection during the task. So you can see this is the green robot, and now it's in a completely different place than it had initially planned, which was to go up here. We demonstrate a typical result of our control strategy with now 4 robots in what we call a formation instance. So here's a representative example. These robots are moving in formation to their goals. and their start and goal yaws are set as 0. So you can see initially that the two robots on the right, these two, don't have visual contact with the robots on the left, and neither does this bottom one have visual contact with the one above, or this top one with the one below. You can see that the cones are not wide enough. The robots gain visual contact with all neighbors, as you can see in panel D, and then they maintain it during the task. They even maintain visual contact at the goal, even though the goal yaws are set to 0. Thus, the robots automatically form visual contact and maintain neighbors within their field of view until they reach their goals, demonstrating a robust control strategy. Here are some quantitative results. On the left are results from circle instances, and on the right, I will show you results soon from what we call the formation instances. We compare against a baseline, which is a PD controller with critical damping as the desired controller certified by the HOCBF constraints with the same velocity and acceleration limits. So these ones on the left here, the first three kind of pale colored ones, these are the baseline results. We compiled results with different field of view angles, beta H, from 120 degrees or 2/3 pi, 4/3 pi or 240 degrees, and 2 pi or 360 degrees. And also different slack variable decay factors, gamma S, as 0.2 and also 0.1. These statistics are averaged over 15 trials. We compare the success rate, which success is defined as all robots reaching their goal area and staying within it without collisions given a time budget. The make span, or the time spent by all robots to reach their goal areas in successful task executions. And the percentage of neighbors in field of view, or the average percentage of neighbors the robot maintains in its field of view during the task. Note that when beta H is 2 pi or a full 360 degrees, then the field of view constraints are always satisfied. The desired goals may not satisfy the visual contact requirement, so as I mentioned earlier, our control strategy compensates for such goals and maintains visual contact but deviates slightly from its desired goal position. Thus, we consider the robot to complete its navigation task if it reaches its goal area and stays within it. For the circle scenario, notice that for up to about 6 robots, our control policy has similar success rate to the baseline. As we increase the number of robots, our algorithm outperforms the baseline, achieving successful executions when the baseline fails to complete the task at all. The reason is that the baseline, as a reactive controller, responds more aggressively to the imminent collisions and does not maintain a large safety distance. As a result, it is more sensitive to estimate uncertainty and exposes the robot to a higher risk of collision once the neighbor detections are lost. For a small horizontal field of view, the control challenge is to maintain neighbors in the field of view, thus providing the latest estimation to avoid collision while reaching the desired goal. As the field of view increases, maintaining visual contact with neighbors becomes easier. However, robots tend to take the shortest path and crowd in the middle of the workspace, and this leads to deadlocks and potential collisions due to uncertainty in the estimation. The challenge of addressing deadlocks in multi-robot planning falls out of the scope of this work, but it's something that we may think about addressing in the future. From the figure, we note that make span decreases as we increase the field of view. The robots tend to take the shortest path as the detection task now becomes simpler. Despite the drop in task success rate, we note that the percentage of neighbors in the field of view maintains above 60% as we scale up the number of robots, even with the small 2/3 pi field of view. Our control strategy maintains the same level of visual contact with neighbors compared to the baseline controller while improving the success rate. Additionally, we evaluate the impact of the slack decay factor gamma S on our control strategy. Notice that less aggressive heading adjustments result in a higher success rate. This result is anticipated as a heading that accounts for neighbors more evenly improves tracking quality in circle instances. In the formation scenarios, since robots move in the same direction, unlike in the circle instances, tasks result in fewer collisions and deadlocks. Overall, we notice an improved scalability and success rate compared to circle instances. Our controller outperforms the baseline across different numbers of robots with outliers in the 4 robot experiments. With a small field of view, the baseline reactive controller satisfies the field of view constraints by compromising goal-reaching capability. In contrast, our control strategy retains goal-reaching capability while respecting field of view constraints. With an omnidirectional field of view, the baseline suffers from collision due to estimation uncertainty as the number of robots increases. In the formation instances, increasing the field of view improves the success rate for both the baseline and our approach. In addition, a larger gamma S works better for formation instances. The make span does not show significant change with different beta H or gamma S, mainly because the task is less challenging regarding navigation. The percentage of neighbors in the field of view again maintains above 60%, even with the small horizontal field of view. Our controller maintains equivalent visual contact quality without compromising the goal reaching capability. With an omnidirectional field of view, the baseline suffers from collision due to estimation uncertainty as the number of robots increases. In the formation instances, increasing the field of view improves the success rate for both the baseline and our approach. Here, I want to show you how our control policy does with a static target. In this case, the quad rotor is keeping the tripod in its field of view while navigating to its goal. So here's the quad rotor, and here's the tripod, and here's the field of view directly from the camera on board the quadcopter. We use April tags to detect the relative position of the target using the onboard camera on the robot. I've circled the quad rotor with a red oval since it's a bit hard to see, but the camera view is clear that the tripod actually remains in the field of view for the entire task. And I'll show you a video of this in a little bit. In this physical experiment with two robots, due to the agile motion of the aerial vehicles and the limited frame rate of the camera on board, we were unable to detect neighbors using April tags. Furthermore, the RGB camera's field of view is about 1/4 pi, thus posing a challenging planning and control problem to maintain visual contact. Instead, we rely on Vicon motion capture to represent neighbor detections. The robot receives the relative location of its neighbor as input to the particle filter from Vicon when that neighbor is inside its sensing region. You can see that the other robot is always maintained in the field of view. Although at this point we aren't detecting the position of the other robot with onboard sensors, we can use a learning-based approach, such as YOLO, to provide more robust detection during motion. You can see that the robots are adjusting their yaw to keep the other robot in the field of view. So here's the other robot circled. And then for the second robot, here's the first robot circled. Finally, here's the video for these experiments. First is the formation instance with 4 robots. In the beginning, you can see all robots are facing to the right, so the ellipses that represent position uncertainty are very high for the robots on the left. After about 5 seconds, the yellow robot has corrected and then the blue robot. There are times they lose visible tracking, but they do correct, and in the end, they reach their goals with full visibility. You can see they lose tracking and then they regain it. And here they reach their goals. Next is a circle instance with 5 robots moving to antipodal points on the circle with low velocity limits. Here they start with all robots in each other's field of view, but it's hard to keep because of the field of view angle and the number of robots. You can see that there are times when tracking is lost, but again, it is recovered. And oftentimes it is lost for a long time, leading to larger ellipses, especially seemingly this yellow robot. But in the end, they do reach a place where they can mostly keep each other in their field of view. The next example is again a circle instance with 5 robots, but this time with high velocity limits. Again, they start with all the robots in each other's field of view, and they do tend to lose tracking again, but they do recover. And you can see that the motion actually is much smoother than for the low velocity limit example. So here's a video for the single robot tracking a static object, the static object being the tripod here towards the top of the feed. And here's the first person view from the camera. And you can see that the robot kind of goes around the side and keeps that tripod in the field of view. So in this case, we are using April tags for tracking. But you can see that the first person view is smooth enough. Finally, here's the physical demo with 2 robots. And you can see the two robots are facing each other as they move around. And in a minute, I'll show you the first person view. But you can tell that they are facing each other and they do maintain the yaw that faces the other robot. So here you can see the first person view from the robots themselves. You can see why the April tags didn't work, as the video feed is not a very high quality. That's more a result of the hardware that we have on board as opposed to the algorithm itself. But you can see that the robots keep each other in their field of view the entire time. So to summarize our contribution, I presented a real-time, robust, distributed multi-robot control strategy that maintains visual contact between robots in communication-denied areas and tolerates temporary constraint violations during navigation. We've also presented a continuous time spline-based trajectory and control generation method that's certified by control barrier functions and an optimization framework, namely MPC-CBF, or Model Predictive Control barrier functions, that solve the continuous time CBF constraints at discretized timestamps. In future work, we'd like to address adaptive CBFs in non-stationary uncertain environments where model uncertainty can be present, and also robust certification with sensor failure and unreliability, and finally long horizon multi-robot trajectory planning with completeness and optimality guarantees with certified behaviors. So if you want to check out the code for this project, you can follow this QR code down here or go to my student Li Shuopen's GitHub page, which I've linked here below. I'd like to thank my collaborators, specifically my student Li Shuopen at Brown University, Mattia Catalani and Professor Lorenzo Sabatini at the University of Modena and Reggio Emilia. I'd also like to thank the National Science Foundation for funding this work. And finally, a very special thanks to the workshop organizers, Naida, Aslik, Pan, and Tikran. Thank you so much for organizing such a wonderful workshop and inviting me to be a part of it, and also for being so accommodating given my travel restrictions. I hope that all of you enjoyed hearing about our recent work. Thank you so much. So the visual contact is the field of view. So the control barrier functions are what actually ensure it. So that slide where there were the three costs, that includes all of that. There's no additional cost. Does that make sense?
Yeah, I guess so. So the question was more like whether keeping the constraints or meeting the constraints ensure like encouraging keeping the field of view.
Yes, so those are essentially maintaining the field of view and also navigating to the goal.
Yeah, thank you. Any other questions regarding?
That's because the safe space that the control barrier function tries to maintain is to keep everything within the field of view.
And I guess I also have one more question to you. It is regarding so you mentioned that you have a specific shape for the obstacles, right?
There's a specific shape for only for maintaining kind of a safety distance. At this point, we don't have obstacles.
Yeah, I mean, yeah, safety distance, that's what I meant. Yeah. But because you're considering a double integrator model, do you just artificially add some shape to it, or do you consider just a point mass?
So that segment where you're trying to keep the other robots in the field of view, you're also trying to keep them a certain distance away from you. So that minimum safety distance between the ego robot and that kind of desired set where the other robots should be, that maintains your safety distance.
Yeah, so you just consider the safety distance instead of the shape of the obstacle, shape of the robot. Is that correct?
Yes, because with quad rotors you have to have a little bit more kind of distance between them anyway. So we don't really consider the exact shape of the robot. But if you were to do this on ground robots, then you could certainly do that.
Yeah, thank you very much. Yeah, there is another question.
I assume I guess you assume you know the surrounding number of robots.
Can you hear me?
Yes, yes, you do know.
Okay.
Yeah, otherwise you wouldn't be able to find them.
Yeah, true. That's true. Yeah, if there are no more questions. All right, let's thank Nora once again. Nora, thank you.
I'm a mathematician, and this is my first talk as a applied work. So be more so this work mostly, so we come up with the idea of game theoretic coordination, and I did the math part, and with help of my colleagues and students, we also did some simulations and actual flight experiment. Yeah, let me start. So this is outline of the talk. I will start the basic motivation, and I will go to the problem formulation and algorithm based on which we did our simulation and did the experiment. So the cooperative flight missions are now getting, because of the recent development of technologies, now cooperative missions becoming reality, and there are many applications like surveillance, monitoring, or exploring new areas, or mapping problems where you need several drones to execute the mission, and there are some many benefits, like with small drones you can, and they're cheaper, and you can if you can properly coordinate between them, then you can get many missions which are not possible to by one drone. And so the multi-UAV missions, we divide it in for multi-UAV missions, we consider the missions which are can be formulated as a time synchronization problem, and for that one we assume that our UAV is equipped with before the mission start, we assume that we have a ground station with which plans and provides a desired trajectory for each of our UAV, and we assume that each UAV is equipped with robust low-level controller, and then we will try to reformulate this coordination, multi-UAV coordination problem as a time synchronization problem, and this is done by concept known virtual time, and this is done, the ideas comes from late 70s, which is the following state-space separation. And so assuming we are given a desired trajectory for each UAV, x, d, I, t, and then we divide our coordination problem to the three-part: trajectory generation, and path follower, and time coordination. So a trajectory generator, which can be a ground station, provides us a desired trajectory for each UAV, and we assume that this low-level controller is quite good, and given the desired trajectory, it can follow quite well the desired trajectory. Now we focus on time coordination problem, how we can ensure coordination. Based on time synchronization, and those are the main assumptions on our trajectories. Like we assume there are space constraints, and there are device physical constraints like speed or velocity. Speed and acceleration are bounded, and furthermore, for the desired trajectory, we assume that there is a spatial separation, so they are not colliding. A priori, we don't design trajectories that they collide. And in this talk, I will present the case that time synchronization leads to the spontaneous arrival, but with similar techniques we can do also sequential arrival or similar time constraint missions. So what is this virtual time? Virtual time is a special concept which allow to somehow by reparameterization of our desired trajectory to get coordination. And this is the idea. It maps actual time to the mission plan time. And let's say we have a so we are keeping track of two times, which is our actual time, and the other one is virtual time. Let's say if everything is fine, there is no any disturbances, or there is everything is fine, then actual time and virtual time, they are coinciding. If let's say there are some because of some disturbances or some other reason there is delay, and the launch of one of the drones didn't happen at the same as the mission starts, then this virtual time actually for this time period, it's always mapped to 0 until the UAV start to fly. It's how this one can help. It's by using this virtual time concept, we actually reparameterizing our desired trajectory. On the left, you can see if everything is in an ideal case and our actual and virtual time are coinciding, then we are there at the trajectory. We are there where we plan to be. If there is something happen and our virtual time not coinciding with our actual mission time, then we are here, but we're supposed to be here. So by using this virtual time, we actually can determine either how we are doing on a mission. We are ahead of mission or behind of mission, and now controlling this parameter, we actually can control how we are doing on a mission. And using this parameter, we can reformulate our desired trajectories. And as you can see, after simple calculation, by using virtual time, we actually can control our speed. If it's let's say if we are ahead of our mission, then we can make virtual time smaller, and we will decrease our speed. If we are behind, we will accelerate. And by using virtual time, we actually can transfer the physical constraint or UAV to the constraint on this parameter gamma I. And beside this coordination, so in a case when this virtual time derivative equal to 1, it means that we are our UAV is traveling with the desired speed that we have. This can be here if gamma dot is 1, then and xi dot gamma equal to x dot. So now the coordination problem actually can be written as following. The coordination problem becomes this virtual time synchronization problem, where if gamma I and gamma j, if they are equal, then they are synchronized. It means that they're going to reach their target at the same time. And to guarantee the desired speed pace, for that one we want that gamma dot I equal to 1. So this is coordination problem for reformulated in a virtual time concept. To get a coordination, we formulate game theoretic approach. So those are the basic mathematical concept that makes sense. Our method optimization problem that we will formulate will be well posed. And this is our game theoretic method. Each UAV tries to minimize, tries to penalize its deviation from desired speed that it should have. And this term, it's penalized the deviation from its neighbors. And the third term, it corresponds to corresponds to control efforts, and it tries to minimize. As you can see, it's become this convex optimization problem, convex game. Yeah, those are the terms that I talk about. This ensures desired speed, this control input, and this is penalized discrepancy between its neighbors. Yeah, so this become a game, and what we did under assumption of fully connectivity. So this is our first result. So if we prove existence of and exponential stability of Nash equilibria under this strong assumption that our communication network is completely connected. However, we develop a numerical method for which we don't need that assumption. It can be very, the network can, only assuming that network is connected in a mean sense, we still have exponential stability of our numerical method. Yeah, this is the theorem. Not only we prove existence, we also derive explicit form of our solution, gamma I, where this power of E is negative. The main idea of the proof is the following. We consider Euler-Lagrange equation of this optimization problem, and then we were able to explicitly solve this Euler-Lagrange equation, and then using which leads to this fourth order differential equation, which we solve using Ferri's method to solve fourth order polynomial equation. Then using the transversality condition coming from our optimization problem, we actually prove the terms of the terms that have exponential growth on our explicit solution, and those terms are 0, and furthermore keep tracking of all. So this is our optimization problem. We write corresponding Euler-Lagrange equation, which become a fourth order coupled system of differential equation, which we are able to solve by decoupling the system, and after considering difference between our gamma i's, which is you remember is the consensus condition for us. The consensus reached when this the difference between gamma I and gamma k is equal to 0. So we get the exact expression for the difference here, and then keep tracking of all terms, the coefficient of this explicit expression on the decaying rate alpha. We were able to prove that there exists positive alpha for which our solution is exponentially stable. And furthermore, this solution actually satisfied the constraint optimization problem that we have. So there exists alpha for which this gamma I actually satisfied the physical constraint that we have on our UAV, on our acceleration and velocity. This is the first part, theoretic part. And now I will go I will go to the more applied side. In this part, we develop so the theoretical result we had more strict assumption on existence and exponential stability, but for algorithm we develop algorithm based on model predictive controller, which also take account path follower errors and communication failures, and even when the communication failures, and if we our communication and is connected in a mean sense. So this is the actually discrete version of the continuous problem that I showed you before. or here we have three. The capital key is the horizon of MPC, and we have here three set of variables. First, S corresponds to our gamma, L corresponds to gamma dot, and gamma double dot corresponds to U, which is our control. And here we have a constraint on our velocity and acceleration, and so at each time step, each of UAVs tries to solve this minimization problem. And here is the communication term. So each UAV shares its future predicted MPC horizon predicted steps, and it's getting from its neighbors only from its neighbors prediction, neighbors information. And the new term here is everything is the linearization of the continuous problem. The only thing new is this alpha term, which actually takes care of the path following errors. And the main idea here is this virtual time concept only defined if you are on a desired trajectory, and so it's if there is a wind or something else, then you may end up outside of your desired trajectory. And there is a question, if you are outside of your desired trajectory, how you define your virtual time. It's actually using this term which defines how you are ahead or behind. You can either add some positive constant to your virtual time, which you actually project to your trajectory, or substitute depending on your from your desired trajectory, ahead or behind of the projection. And furthermore, what we did, we also add to what's the advantage of having this optimization based method. We can incorporate many concepts into the problem. And for example, and also the main advantage of this problem, it's one-dimensional. After doing this virtual time transformation, and our coordination problem, which can be depending on dynamics, can be high dimensional. In this case, as it's become only one-dimensional, it's only t-dependent. And one thing that we did also, we introduced this communication smoothing term, which instead of just having 1 and 0, if you have communication, it's 1, and it's 0 if there is no communication. And we define it's 1 and 0, and here we assume that communication between UAVs is determined by a distance between them. And we kind of give a weight. If you are too far, then it's 0. If you are getting closer, it's smoothly become 1, not it's just 1 and 0. And this actually helps to get rid of the spikes that you are getting during when you are computing your control. Or sometimes if UAV is not in your range and it appears, sometimes it gives the spike to your controller, because before it doesn't see it, and and it's once it sees it, the control may jump up immediately. To mitigate that effort, we introduce this function, and we incorporate this one into our control communication term. Even though this is not non-linear term, but because our optimization problem is one-dimensional, still we were able to solve this problem in real time quite fast. And similar way, we can also incorporate collision avoidance using our optimization problem, which is a similar concept. If UAVs are far, they don't. This term, collision avoidance term, doesn't activate. It's 0 when UAVs or their trajectories are getting closer. Then this term activates, and because of this minimization and problem, they basically play a game, and after playing game, they determine their speed. Actually, they adjust their speed the way that they will not collide. At the end, I will show the video how it will work. Yeah. And furthermore, we also were able to get some result on this algorithm recently for a horizon equal 1 case. We were able to prove that for any initial condition that inside our feasible domain. We have this MPC method, the discrete optimization problem when k goes to infinity, it leads to the consensus, and we are keeping our pace. Furthermore, this algorithm is actually exponential stable because of this identity that we have here. Yeah. And general idea of the proof of this is the following: because we are in a quadratic convex game, we were able to explicitly solve the equation and find our control in terms of S and L. And after that, after solving for a U, we start to look the terms which are our consensus parameter. And we will find out that those are actually become recurrent expression, and where recurrent expression with a matrix A, and we keep track of the explicit expression of this matrix A, and we find out that this is actually construction mapping depending on our discretization and size, H. Yeah, and we prove that actually this discrete program is exponentially stable. Yeah, this is the algorithm, how it works. So let's say we are given n UAVs. For each of them, we are given we know their initial virtual time, and we know their initial speed. Then, and for each of them, we predict some. Our MPC horizon is K should be. Yeah, so our MPC horizon is fixed. For each of them at the initial state, we do some guess for their future MPC steps, and then and then we are solving optimization problem, and after doing getting our control, we go to the next step, and then we are getting information from our neighbors about their future MPC steps, and again we are now resolving again the same optimization problem, and at each time we are incorporating path following error at the initial state of our problem. In this discrete problem, we only are incorporating path following error in an initial state, which makes our problem always convex. So at each step, we are always solving a quadratic optimization problem. This is the main thing that make our algorithm run real time. Yeah, this is general idea, and so I will show also video. In the following examples, you will see that there is ideal path following and ideal communication, and UAVs are launching with different initial times, and they will get exponentially to the stability. You can see their gammas are synchronizing quite fast, and gamma dots. And similar, if the communication has failures or non-ideal communication, we are getting again exponential stability, but there are a little bit delays. And in a case of wind, it's same. Only the time that we reach to the consensus, it's again delayed. And this nice example about collision avoidance that we incorporated, and these are some references, and let me show you the video. Yep. So the UAVs start from different positions, and as you can see, they're synchronizing quite fast, and those are done by my students. I haven't done anything here, so mine is only math part. In the second case is non-ideal communication, so communication fails. Again, they're reaching consensus quite fast. And as you can see on here, when there is an ideal communication and ideal path forward, then they reach the consensus at 3.2 seconds. But now, because of the communication error, it should be less. Okay, sorry. And in this case, you can see the effect of wind. Again, it's incorporated to the optimization problem, and because of its quadratic, it can be solved quite fast. Yeah, you can see that it almost twice delayed the reach of consensus. And this one was the this one, one of the advantages to considering optimization-based coordination problem. So we're incorporating the collision avoidance into our cost function. And in this example, so the UAVs, there are 6 UAVs that each of their trajectories designed that way that they ideally should collide at this intersection point, but because of this optimization problem, they play a game, and as you can see, they're adjusting their speeds, and they're crossing without collision. And here you can see the minimal distance between UAVs; it's always positive. Yeah, and after passing that collision point, they're again getting to the consensus. And here on the left, you can see their consensus, and then this collision part, again consensus, collision, and consensus. And there are 2 real flight experiments which are done by at the group of Naira Hovakimian, Mikhail Aramyan. He's a PhD student with Naira Hovakimian. So he did this all stuff. So the idea, we have 4 UAVs, 2 of them doing this circular movement, and these 2 are doing yin-yang, and they're intersecting at this point. Ideally, they should collide, but again, having our optimization-based method, they play a game. They play a game, and they adjust their speeds, and they avoid the collision. And as you can see, again, here consensus, then there is a collision avoid period, and here they because one in front of the second, the first one should be always faster than it's supposed to go. That's why here we have this situation. And the last one is more challenging. We have 4 UAVs that are supposed to collide at one point. They're moving in different circles, but all these circles have one common point to intersect. So we designed the way that they, in this part, in this part, they are in a consensus, so they are coordinated. Before entering here, they are adjusting their speed, and inside the small circle, they are going quite fast. And then again, adjusting their speed, they are exiting inner circle. And then after that, again, they are getting the coordinate. Yes, as you can see, this first part, they were, and all these simulations and all these real flight experiments have done with the communication failure. So as you can see here, even though they are different because we somehow push them go faster than a priori we define. That's why we have here big gap, but actually they are in consensus, but consensus with a higher speed profile that we designed. Okay, this is all. Thank you. If you have questions, I'm happy to answer.
Any questions from the audience?
Yes. Yes.
So for the, I guess in the simulations, you showed the minimum distance between the
Yes.
drones was always greater than 0.
Yes.
Would it be possible in this framework to, like, if say if you wanted to have a minimum safety distance, for example, like if say in a certain such scenario you wanted a minimum distance of 1.5 meters, for example, is that something?
Yes, it's possible. Yes, it's possible. The only thing we need to design that way. So the cost function and the constraint. So it's possible. The only thing it's design thing that we need to change. Okay, thank you. Other questions? Yes.
Thank you very much for the talk. I'm
Yeah.
really enjoying it.
Thank you.
To be honest, I'm not familiar with the game theoretic approach.
Uh-huh.
I'm also doing research about UAV coordination.
Okay.
Using calculation control and CDF base. My question is, what is generally, like using the game theoretic approach, like the advantage of like the common method, for example, like for pathfinding or that kind of things?
Sorry, what method you were using?
Yes, so my question is, I'm not familiar with the game theoretic approach,
Uh-huh.
but I think it's very interesting. I'm going to learn and read more about the
Okay,
detail of the
thank
work.
you.
Generally, like, what is the advantage of the game theoretic approach that we are using to solve
Yep.
the problem here over like the standard common method?
Yeah, common method, you mean consensus or this PID or OD based method? Yeah, the first thing is you can ensure optimality here. So you are basically solving optimization problem. The next thing that you can also design a optimization problem the way that you can, for example, optimize energy efficiency or this collision avoidance. Collision avoidance, it's like something free that you can get, or other. Like it has inside logic, which you cannot do in a case of consensus-based method. Yes, in a consensus-based method, you need to plan it really carefully to satisfy some, how to say, ongoing mission requirement. I don't have here, but the main thing is we have this. How to say it? So there is a that the common method that you are saying, those are mostly relying on pre-computation. Yes, you are designing whatever you want, and you are trying to adapt in a changing environment, but you are not optimizing, or you are not you are not optimizing, or you are not adapting real time to the environment, which in this case, if you give for example, this collision avoidance cost function, then it doesn't matter where you are or how a priori trajectories are designed or something else. It has logic inside it, and you run, it will take care of it.
Thank you very much.
Yeah, thank you too. So there is no other. Yes. Yes.
Okay. So in terms of local, what are they computing locally, or what kind of sensor information from neighbors?
Those are crazy flies, so nothing on board. So it's centralized, decentralized. So there's. I'm not 100% sure how it works, but basically it's like this. You are sending command to the drones to follow the path, and they are going there, and they are sending back to the command center, and there we are basically solving this optimization problem in a distributed manner, and then we are sending back solution. And what we are solving is these virtual times, and each of UAV, so we fix this MPC time horizon. In our case, I guess it was 10. So each of UAV, they are solving this optimization. Yeah. Yeah, we can see here, so that they are solving optimization problem, and then they're broadcasting their future virtual times, and each neighboring it's getting that information. And beside that, you have this path following error. Each of UAV estimate where it is, and it's compute how path following error, how it's big. This is in alpha term, and then so this more than enough. So you have information. Let me show here. So this is information and MPC future time steps that you are getting from your neighbors. And this is the parameter that you want to solve for that. And this alpha is you are at each step you are computing how big your path following error. And this optimization problem now become only depending on L, S, U. And you solve for that, but it
Central command unit.
no. There is no central command. So you are getting information from your neighbors here, and then you are solving it locally in your UAV, which we didn't do because this crazy flight. But we because of this issue of design and having I don't know the hardware support for these small UAVs, we did it, but we keep this distributed like feature. Okay, thank you.
So, and for the feedback, you are using Viken, right, to get the...
Yes. Motion capturing system, yes. Okay, if there is no... Yes.
How do you get the future information of your neighbors? You only know the, for example, with package, customer key, you can get the information of your neighbors key. So how to get the future information?
Yeah, like for...
Next step and then next step, or your time horizon.
Yeah, so for... okay. Once you solve this optimization problem, you are getting a vector of gammas with a capital K length. And then when you go to the next step, yes, you're right, there is something. So when you go to the next step, you are now you have K minus 1. Yes, you already use 1. We either keep the last one constant and you broadcast that one. So it's when you are solving, you are getting this SK, which is K. It has capital K length. You keep that whole. You only for MPC you only use first control. Yes, you basically use your first control input, and but you have whole horizon. So what we do, we keep this whole horizon. We go to the next step, and we start to broadcast what we computed in the last step. And the UAVs are from your neighbors. They are taking that information and they are putting it here and solving the optimization problem again. And because you did this at each time, eventually you are getting that you are converging, even though you have this mismatch between your steps, but it's convergence. Yeah. Welcome. Thank you.
My name is Venanzio. This presentation is going to be about our work on cooperative autonomous systems. So I like to start, and I am an associate professor at the University of Iowa. I like to start with a brief overview on what we do in our lab. What do we mean by controlling cooperative autonomous systems? In particular, I will focus first on our work on motion planning, then on coordination. There'll be a lot of similarities with what you just saw in the previous presentation. We work with the same group of people, so I guess I will present how we solve a very similar problem using more standard consensus methods and the results we get from there, and then I land with some conclusions. So let's get started with the overview of the lab. We work lately a lot on underwater robotics, because we are in Iowa, and that's very weird that in Iowa we work on underwater robotics, but actually there is a huge center for fluidodynamics research, and there is a lot of underwater vehicles to be studied and lately to be controlled. So lately that's been a lot of our focus. By training, I am a drones person and very passionate about multi-drones type of controls. And lately, I also got some interest in continuum robots and soft robots. So this presentation will be about CAS, but if you are interested in this stuff and you want to chat, we can definitely do that. What's the problem with cooperative autonomous system? Well, at least what's the problem that we want to solve? So if you go and look at the literature on cooperative autonomous systems, there is a lot of them, especially in the past few decades, but most of the literature focuses on specific problems. So there is a lot of stuff on formation, flocking, coordination, and so on. The point we started at is we wanted to develop a framework that is flexible enough and capable of accommodating all these types of missions. Examples that we have in mind is air sampling missions where you have multiple drones, they have different sensors on boards and they have to gather data and they have to exchange position so that they gather different data at some specified frequency, or saving victims in avalanche scenarios when you want multiple drones to localize a victim as soon as possible, search and rescue, and entertainment. You know, there was a buzz about having drones in Super Bowls or Olympics. So these types of multi-agent missions. This led us to work on this specific framework, which is mainly the subject of a book that we published back in 2017, which of course still has several open problems. But the framework is based on these two main blocks, motion planning and coordination. The idea is to have a motion planner that is efficient enough and safe enough to generate trajectories for all these vehicles that are safe, they conflicted, and they reach some objective while minimizing some cost function. And then on top of this motion planning, you have some coordination type framework which regulates the speed of each vehicle so that they can react by adjusting their velocity to some event that maybe some obstacles, pop-up obstacles, or change in the mission. And so let me first focus on what we did about motion planning. So at the end of the day, motion planning for multiple vehicles can be formally stated, I guess in its more general form, as nonlinear optimal control problem. So you have some state X and U, part of X is your trajectory, you have some general nonlinear cost function, you have your differential equations, x dot equal fxu, that drives the dynamics of the system, nonlinear constraints and terminal conditions. How do you solve this? Well, you don't, because there is no analytical solution, and of course, depending on how complex these functions are. So the only way you have to find an approximate solution to this guy is applying some numerical method. So one type of numerical method, such as pseudospectral methods, they assume that your trajectory is actually not any nonlinear function, but is a polynomial. Now, polynomial is represented by a limited amount of coefficients. You can discretize these polynomials at several points along the trajectories, and then you optimize over the coefficients of the polynomials and apply the constraints at some finite amount of points. Okay? Well, there is a problem with that. And these mainly, well, there is several problems with that. One of the main problems is the huge trade-off these methods have between efficiency and safety. So what do I mean by that? Let's consider this example where you want to generate a trajectory from A to B. So the state is your trajectory, the input is whatever tracks that trajectory. And you want to avoid these 4 obstacles, right? So let's say we want to avoid these 4 obstacles and generate a trajectory using a 4th order Lagrange polynomial, which it's a polynomial that interpolates the points. These are 5 points. They would return a feasible trajectory because none of them collides with the points. However, you interpolate them, you have a collision, right? Well, but that's easy, right? We're just using 5 points. We should crank that up, and then you get a safe trajectory, right? But what happens if you actually have multiple vehicles? So already at this point, if you use certain optimization algorithm to ensure rigorously ensure safety, your algorithm may already become slow. But if you have multiple vehicles where each of them have to avoid the obstacles and each of them have to avoid each other's points, then the problem may easily become intractable. Okay? So the trade-off I'm talking about is described in this plot, where to reach your safe line, here we are talking about aerospace applications where you want to be very safe, right? To reach your safety line, you should crank up your order approximation. However, that slows down your algorithm. We looked for a method that doesn't exhibit that trade-off. And especially in that plot, we are on the red line. Whatever is the order approximation you choose, your trajectory is always going to be safe. And we kind of looked into these Bernstein polynomials, which are a specific class of polynomials, like, okay, Bézier curves, same thing, which have very nice properties, which can be used for us to ensure that we are on that red line. So, for example, good thing about Bézier curves or Bernstein polynomials, they lie within the convex hull described by the control points. All right? If the Bernstein polynomial is, I don't know where is my, if the Bernstein polynomial is described by these 6 coefficients and you build a convex hull, for sure your trajectory is within that convex hull. So if your convex hull is away from an obstacle, for sure your trajectory is collision-free. You can apply the Castle-Jau algorithm, a very numerically efficient and robust algorithm that splits your Bernstein polynomial into 2, which makes this approach less conservative. And you can keep splitting and splitting until you actually end up finding in a very short time what is the actual distance between your curve and the obstacle itself. So we kind of took all these properties that Bernstein polynomials have. We made our own algorithms to find all these things, and they can be found on our GitHub website, where we have a few. We have Python, C++, and MATLAB version. So that's a thing. We also looked at the numerical properties of this method. So consistency of approximation. There is a huge literature on consistency of approximation for optimal control methods. What does consistency of approximation mean is you have an optimal control problem, nonlinear problem. You approximate it by some function, in this case, Bernstein polynomials. Well, the first question is, for your order of choice, does the approximated problem have a solution? And as you crank up the order of approximation, does the solution converge to the actual solution to the original optimal control problem? Okay? And so this paper and this proof actually provide bounds, and if you want, very conservative guidelines on how the order approximation could be selected to have your problem feasible, and guarantees that actually your approximated problem will converge. What is the disadvantage? Bernstein polynomials are super slow. So Lagrange polynomial, for example, which are widely used in pseudo-spectral methods, they converge to a rate 1 over n to the m, where m is the order of the Sobolev space to which the function belongs. In words, the more the function is well-behaved, continuous, the more fast your Lagrange polynomial will converge. Bernstein doesn't care about how nice is the function you're trying to approximate. He always converges to a rate 1 to the 1 over n. Okay? It seems, though, that the fact that Bernstein doesn't care about how nice the function is, it kind of results in Bernstein being nice if the function is not nice. Well, this is, sorry for the lack of rigor. It just came out like that now. But it turns out that when Lagrange polynomials are trying to approximate this continuous function, just Lipschitz function, Holder continuous function, they do not converge. For example, for steps, they exhibit the Gibbs phenomenon, and they will never converge to the function they are trying to approximate. It turns out that Bernstein polynomials are really smooth, and this is kind of a point in favor of the optimal control audience, because most of your optimal control problems will actually be bang bang. And so when you go approximate your input, you actually get something smooth and not an optimization algorithm that would diverge or will not return a solution because the polynomial is kind of going crazy. This is just a picture showing how nice Bernstein, despite being much slower, how nice it converges to step functions versus the Gibbs phenomenon that Lagrange polynomials exhibit. Few applications, few things that we have done with these Bernstein polynomials. On the left-hand side, some traveling salesman problem where they are trying to optimize the trajectory from a station to another. We are recently working on US integration near airports where multiple aircraft should take into account pilots' behavior in order to loiter around the airport and wait for the FAA approval to land. This is some online motion planning. If your problem is simple enough, you can solve your optimal control problem in milliseconds, which means you can apply it in an MPC fashion by providing a new trajectory every time another obstacle is observed. We have worked on avalanche victims scenarios, of course, underwater robots, target monitoring, and swarms. And this is the QR code for our GitHub, where you can find these examples and the code used to generate it. A few new directions. Well, if you now can use a Bernstein polynomial to represent the solution to ODE, what about using a Bernstein surface or even on more dimension to approximate the solution to PDE? The inspiration of this came from the work that we did in continuous robotics, when we want to replicate a robot that moves like an octopus arm. And so the octopus arm dynamics can be represented by a Kossert rod that is a PDE, okay? So we started looking on how to use a Bernstein surface to represent the dynamics of this rod in time and also in the space variable, and use this now to solve this partial differential equation. You end up planning a surface that is the robot arm that moves in time. But then we said, how about this solid object is actually a swarm of vehicles? For example, living in a plane or living in a solid, okay? And so these are a few results. This is from Mac's thesis, a PhD student that just graduated, showing how we can represent Bernstein swarms using Bernstein solids and use cost functions like splitting to avoid an obstacles, or splitting just because, or maintaining formation to avoid an obstacles, and so on. And this is actually not available yet, but it's been submitted to CDC, so we'll see in a month if it will be available soon. Another student actually raised the point. Well, your problems now are so big. This problem right here, for example, the student left the algorithm for 20 minutes, and then 20 minutes after the solution is ready, right? So you cannot apply in real time because they are so huge. So the student, this other student raised the point that said, well, there is a solution that I can generate in 20 minutes, but what if I leave it overnight or over the week or over the month? Well, at least I get a bunch of solutions that I know solve that specific problems. And if I formulate my optimal control problem with a bunch of parameters, these parameters can become the input to a neural network, in particular a transformer network, because now there is a buzz about transformer networks. We use ChatGPT to write emails, why not to generate trajectories? So he kind of used a couple of examples where he solved the brachistochrone problems several times, generated data of 1,000 trajectories, and then asked the transformer networks for a given initial and final position, what's the solution to the brachistochrone problem? And found that the algorithm is quite good at approximating the solution, and then he did the same for motion planning. He has a bunch of generated trajectories avoiding one obstacle, and then he says, well, I can ask for each time step how to generate a new trajectory, and then attach them together and perhaps solve more complex problems. And this was definitely applied. So this is Gage. This is the student that had this idea. And this is applied to the problem that is his main topic of his thesis, that is generating trajectories for near airports, where we actually do have a lot of data from pilots. We can generate more data from NASA software that is developed this software that kind of replicates the behavior of pilots near airports, and then we can use this to generate trajectories. And of course, you don't want to generate a trajectory using a transformer and then give it to the UAV, but the main idea is to at least use it as an initial guess to then your optimization algorithm, which will hopefully be much faster. So very new directions, results developed in the past few months, as you can see, also submitted to aviation and CDC, and we're waiting for that. How, 5 minutes?
No, 15 minutes.
15 minutes, oh, great. So let's skip to coordination now. We have seen something similar, so the same idea as before. You do have a trajectory, which is now generated by, let's say, Bernstein polynomials. Now you split this trajectory. You split it in a space part and a time part, okay? So the spatial features of the trajectory remain the same, but what changes online is the way you track this desired path. Let's call, just like before, the variable virtual time. And let's say for different speeds of the virtual time, you're going to have different trajectories. And actually, presentation was very nice because it will allow me to skip a bunch of details. But just like before, you have your problem. You want the gammas to all be the same and coordinate, and you want the gammas to follow some desired rate. But now let's say that this desired rate is only known to a few vehicles. So you have, let's say, one leader or two leaders. They know what is the desired rate that they all should track. These are the readers. They have a separate controller that governs the motion of these variables that you want to track. And then you have the followers, which go and track them. So similarly to the game theoretic approach, we formulate this consensus problem and addressed it using standard Lyapunov theorem. So the end of the story is this. You have your control input is the derivative, the double derivative of the virtual time. So this is a bunch of integrators, right? The acceleration of the virtual time is the input. And they are defined as PI controllers on these coordination variables. And these gains is what ensure that consensus is reached by the gammas of all the vehicles. At the same time, the integrator also ensures that even without knowing the target rate, also the followers will be able to follow the desired speed. Formulating this problem into a Lyapunov framework, we also do assumptions on the communication graph. So we say that, start the Laplacian of the communication graph. We say that the graph is not connected necessarily, but is connected in time, so they may not talk at all for a bunch of time, as long as point-wise they exchange information. The information they are exchanging is the virtual time. And in time-continuous framework, this is actually the persistency of excitation assumption. So for a piece of time, capital T, if the mu variable is greater than 0, it means that in that long time frame, they have communicated at least a little bit. The higher is mu, the smaller is t, the better they have communicated. And the beauty of framing this into a Lyapunov theoretical framework is that your actual result then shows how the capabilities of the vehicles to coordinate actually depends on this quality of the communication network. So you have exponential stability in the case where there is no tracking error and there is no saturation, blah, blah, blah. Otherwise, you have more complex terms. But let's assume that you have exponential stability because everything works. Then your rate of convergence is actually dependent on the mu and the inverse of t, which means the better you communicate. So if you give me, for example, the quality of your network, if you know beforehand how your vehicles are able to communicate throughout the mission, you can use that information to plan your trajectories or to have some guarantees about some stuff. And as I said, let's ignore for now tracking performance, but these results also take into account when the vehicles are not able to actually track the trajectories. A few examples. So these are fixed wing UAVs. These tests were done in Camp Roberts in California in collaboration with the Naval Postgraduate School. 2 fixed wing UAVs. They are tracking this road, and the objective of coordination is to coordinate, of course, to coordinate along the trajectory and take pictures at the same piece of the road. And these are pictures taken every 1 second from the camera's position under these UAVs, which show coordination. And now you can even extrapolate these results to different applications, where perhaps the coordination variables you want to coordinate along is not necessarily the virtual time, but is the line of sight of the vehicles to some agent that is moving on the ground. So in this case, the same 2 fixed UAVs are moving along with the ground van on the ground, with the van moving on the ground, and they are coordinating their line of sight to the vehicle. So they always maintain a desired phase shift. Other results, this shows what happens in a swarm. So for example, you have a swarm of vehicles, then you have one of them fails, it breaks, everyone keeps moving because there is no conception of coordination here, and so they are not able to react. They should replan new trajectories when that happens, but there's no time because the computational load of motion planning may be too high. So you can use coordination in this case so that when you see on the right plot, when failure is detected, and so one of the vehicles slow down, all the other vehicles, by means of coordination, slow down and keep going at a slower speed to maintain everything safe. This is the same experiment done in the lab with the 4 drones, where there is 2 additional obstacles. So trajectories were generated for the whole fleet, 4 of them, and at some point I don't see the graphs, but that's what I'm. And this is another scenario when the input, the exogenous variable to the system that makes them slow down is actually the perception from one of them, the drone in the center, of an external fleet that is coming. So these guys are going at constant speed. The one in the middle is the leader. At this point, the one in the middle sees another fleet coming, which you don't see now, but it's coming in a little bit. And this fleet is going to collide. So they decide, the leader decides to speed up the mission by changing the gamma d dot variable. So all of them then keep coordinating on this newer variable, resulting into avoidance of this upcoming fleet. And another interesting twist proposed now by Camilla and Mia. Camilla also just graduated, and Mia is a new PhD student. But now all this happens if you assume that the communication is indirected, meaning if I talk to you, you talk to me. But what if we formulate this framework in a vision-based scenario, where, for example, the obstacle you saw in the slide before was detected by a visual sensor. That means that, in this case, if you see me, that doesn't necessarily mean I see you. So we want to incorporate also occlusions scenarios, but also scenarios in which vision-based sensing is not omnidirectional, but you can only see in front of you, and so the one in front of you doesn't see you. And that leads to reformulating the whole thing, which now falls apart when you consider directed graph, and generating new proofs. So this was also recently done in a CDC paper. Now we're working on, on the journal version. And I'm not including the results in these slides, but we have the same assumption, persistence of excitation, very similar, but it's the parallel for directed graph. And we kind of conclude the same results, where all these performance are in fact functions of how well they can communicate, or in this case, see each other. And this is the flight tests. So what happens in this case, so in this case, every vehicle is going on their own direction, and if they keep going, they will cross each other and crash at one point. So at some point, one of them is able to see the one on the right, so they can only see the one on the right, for example. So they are able to generate online a kind of roundabout, which is what we do maybe when, and then coordinate their line of sight on this roundabout until they reach a point closer to where they were going, and then forget about collision, keep going in the I guess, I don't know if you have seen, we had some limitation, hardware limitation. We could test only with 4 vehicles. And this is a simulation with 16, I guess. But of course, everything is online, decentralized, so this, the theoretical results also hold for any number of vehicles. Concluding remarks. I have talked about motion planning, motion planning, where we presented a flexible framework that allows for the solution of general nonlinear optimal control problems, which can be used for motion planning. The main thing is mitigating the trade-off between safety and computational efficiency. So the main message is we can solve optimal control problems even with low orders of approximation. We can give up on the cost, but we can guarantee safety in a rigorous manner. And for what concerns decentralized control, we have boiled down the problem to a consensus problem, solved it using consensus and Lyapunov arguments, and found bounds and performance guarantees based on the communication capabilities of the vehicles. This is an incomplete list of acknowledgements, funding agencies, and the students, collaborators, and I'll be happy to take questions.
Yes, thank you.
Yeah.
So the vision-based one that you said they go circles or trajectory, actually already defined why they go circles. The vision-based.
They do circle because in this case we decided to do circles because we were thinking of a roundabout scenarios. But they could have already generated the trajectory, as long as these trajectories intrinsically lead to collision avoidance if line of sight is kept. So the circle in this case is a more natural thing.
So it is the same principle. You have generated trajectory and then you align with this line of sight.
Same exact principle, with the only difference that now this required the extension of these results to directed graphs, because now the information is not communicated, but the information is sensed.
I do have a question, two questions actually. One of them is regarding the transformer-based ones. Why transformers? So that's the question.
Yeah, the transformer net, so that's an interesting question actually. We found that for solving the Bragi-Stockron problem, feed-forward neural network actually gets the same performance of a transformer network, because the trajectory is simple enough, and so data, you don't need a lot of data. But for scenarios like this one, where trajectories are more complex, you need to be able to feed your network with as many trajectories as you want. And you don't want your network to start diverging where you have too much data. And
Is this right in RNNs? Because it feels like if it's a trajectory, like recurrent networks should be more kind of appropriate.
well, so that's, yeah, again, that's a good point. We are actually using a transformer network in a RNN fashion. So this actually, the inspiration came from this paper where they're using transformer for MPC. So exactly as you said, it's not predicting the whole thing, but just the next step, and then using the previous data to predict the next point.
Then it makes sense.
So we are using transformer networks in a RNN fashion. But the next step is now to actually compare it to vanilla LSTM or, yeah.
Then do you need, like how much data you need to train those kind of?
So for these trajectories right here, we are using 100,000 trajectories.
Mm-hmm.
That's the amount of data.
Trajectories and not sample points.
Trajectories.
That's lost.
Yes.
Yeah.
But the point is that because we can, right? Because I leave the thing on Friday, and then I go back on Monday, and I go to the student. Here is your 100,000 trajectories, and I didn't do nothing. Okay.
Right. And one more question regarding the last part of your. What is the computation burden for this? Because you mentioned that you had some hardware issues. Was it related to the computation power?
So the computational burden for purely coordination is 0, because these are control law that you apply in real time.
Yeah,
but the problem.
Vision part especially?
Sorry?
Because you also have the vision part.
Yeah, because you also have the vision part. Then there is a bunch of computation for issues that we are not addressing now. That is, detect, given so many vehicles, where is going to be the collision point, in which order they should have. For now, we are assuming that we have a collision point. We are assuming that we can generate circular trajectories, and that you can do easily with piecewise Merson polynomials without computational burden. But yes, if you only use vision-based, then how do you find that point? How do you find how many vehicles? That is
First of all, thank you for giving a chance to give a presentation about my work. I mean, basically the arrow names asked me to present our work in this workshop, so I'm gonna present our work about safety insured model applications under model uncertainty. So I will introduce myself briefly. I'm Lee Kim, and then I'm working in S2 Robotics as a postdoc. My research is around safety critical systems and general robotics. And recently I'm working on, I'm diving into the in-hand manipulations with safety guarantees. Yeah. And then these are contents. So I'm gonna introduce briefly about the S2 Robotics, and I'm gonna give you overview about why we should ensure the safety guarantees. And then I'm gonna introduce, of course, control variable functions. And then the rest of my presentations are about the challenges for the research and the applications that we developed. Okay. S2 Robotics is in the Odense in Denmark. It's a very small city, but it's getting bigger and bigger. So we have a very close collaboration with industrial companies like Lego, Novo Nordisk, and Universal Robot, and so on. We would like to solve some problems that they would like us to solve the problem. So we have over 65 employees, and then we are still hiring the good researchers like you. And then if you're interested in our section, you can go to our website and you can get some information about some job. All right, I'm going to give you some overview. This is a scale robot. And I programmed the motion control over there, and it fails because I didn't know about the safety guarantees 5 years ago. So I just used the motion predictive control with a zero moment point. So let's say, what if we have some very safe critical systems like fusion reactor robot manipulator? Then it's gonna be disaster. This is just for fun, right? I spent a lot of time to fix the robots after this one, and then I got some blame from my supervisor, but that's okay. So why should we consider the safety? You might already know we need to protect human life, and we need to make the system reliable and trust, and then we need to increase the economic efficiency. So how can we ensure the safety guarantees, formal safety guarantees in robotics? Of course, we can use the artificial potential field of virtual fixtures to ensure safety guarantees for the collision avoidance. But the problem is that they don't have any the formal safety guarantees like a rigorous proof of the safety. So I will give you two examples for the control variable functions. The first one is drone systems. I saw a lot of the drone application in this workshop. Let's say we have the drone model over there, and then we want to generate a safe trajectory to avoid the cylinder in red. How can we generate that trajectory? We can use the control variable functions to achieve the collision avoidance path planning. On the other hand, few cases have investigated the contact force regulations with the control variable functions. Let's say this is a very familiar diagram in this conference. If we don't have any safety controller, and then we can just use the PID controller to regulate the contact force between the robots and for example, the table. Then you can see this figure, and we can have some oscillation, and as well as we have some safety violations if we have some minus 10.5 safety limitation here. But on the other hand, if we use the control variable function with the environmental model like a spring damper system, then we can regulate the contact force like this in the green line. So these are the two examples to understand the control variable functions. As you might already expect that the control variable functions are based on model-based one. So we should have model like this. This is control affine systems. So I'm not gonna explain the detail because most of all knows the control variable functions or what the control variable functions are. So let's say we have the safety set that has a safety set h of x. It should be equal and greater than 0. And if we generate the control input satisfying this constraint, then we can ensure the safety. that's the theorem. And then we can also use the quadratic programming with this constraint. So next question is that how can we obtain these ones? We can think about these simple examples. So if we have h of x values, and then we can design the exponential curve, then these equations, solutions, that h of x never hit the 0, which means that we can ensure this one. Then we can ensure the safety. So that's why we enforce this constraint, the quadratic programming, and then we can ensure the safety. This is the basic concept of the controller functions. But as you already know, the controller functions, if we use the controller functions, the safety guarantees will be violated if we have parametric uncertainty, right? Non-parametric uncertainty, input disturbances, input delay, and complex load dynamics. So in this talk, I will focus on these 5 things. The first applications is contact force regulations. So we apply the controller functions into the policing applications. And then finger grasping, it looks like a human the hands. And then from the input delay, we apply the controller functions to keep the safe distance between 2 vehicles. And lastly, we also apply the controller functions things into the medical robotics, because the medical robotics, the safety is very, very important in here. All right. In the contact force regulation, we developed some method to deal with the non-parametric and parametric and non-parametric uncertainty at the same time. As you already know, we can use, let's say, robust approach, adaptive approach. There is an existing work in here. Then we can generate the safety control input satisfying this one, then we can ensure the safety if we have only parametric uncertainty. But what if non-parametric uncertainty exists in the equation too? Then we need to do something more. So this is a very simple idea. We combine both of them, the model-based approach and data-driven approach. Data-driven approach is Gaussian process controller functions, and then we combine both of them into the one framework. And then this is the result. And you can see our papers via QR code here if you're interested. And then we have some comparison here. Normally we can use the Gaussian process controller function here, but if we use our method, then we can reduce the conservatism here, and then we can reduce the uncertainty of the predictions from the Gaussian process. These graphs are about the standard deviation from the Gaussian process. As you can see in here, it's very small compared to the original one. The next thing is we apply the controller functions into the policing applications like this. So how can we apply that? Let's start with the quality guarantees. In the policing, the quality guarantees is very important. The references should be uniform over the surfaces. So how can we define this one? We can use the material river weight models, and then we can define the admissible guarantee ranges with a material river weight here, and then as you can see in this, these equations, we can calculate the contact force set here. If we regulate the contact force within this set, then we can guarantee the material river weight. So we can achieve the quality guarantees. This is the main idea of this work. So how can we do that? As you can see in here, the safe set is time varying. So we need to do something more on the top of the standard controller functions. Okay. So luckily, the good researchers already proposed the time varying controller function here. So we're going to use this one, and then we're going to use the robust adaptive controller function as well. And also in the robotic systems, even if we control the contact force as accurate as possible, we're going to have disturbances in here, right? So we introduced the input to state safety. We used these concepts in our framework as well. So you can find all these theorems on the Google. So I'm not going to explain the detail here. Yes. So simply we just combine the 3 of them in one framework. On the top of that, we also use the set members verifications to reduce the the uncertainty of the maximum bound of the parametric uncertainty. So this is a data-driven method. And as you can see in here, this is very proof concept experiment. When you use time-varying controller functions, it violates the guarantee ranges here. On the other hand, if we use our method, since we have a robustness against the uncertainty, then we can guarantee the ranges here as well. And then if we use the set members identification to reduce the conservatism, then we can expect that the conservatism is reduced, a little bit reduced, when we look at the h of x functions graphs here. Yeah. So next one is finger grasping. I mean, basically the concept is similar, because so we want to control the contact force. So we want to control the contact force between the two fingers. So this work is a collaboration work with Aerodynamics Lab. So the motivation is, how can we grasp a fragile object safely? To the best of knowledge, no one tried these controllable functions into the robotic grasping. I don't know why, because it's a little bit simpler than the others, the complex applications. So we have a controllable functions, we have model uncertainty, and then what should we do? So basically, we can just design the control loop like this. We have a nominal controller, like a PID controller, and then we have some finger force controller here. And then if we estimate the contact force and contact torque from the tactile sensing, then we can control the contact force, and then we can have a margins to ensure the safety. However, there is no formal guarantees in here. So in our framework, we have several safety filters: standard method, standard controller function, and robust update controller function, and robust controller function, and lastly, disturbed observer-based controller functions. Yeah. So this is the result. We tried a full object. I mean, it looks very simpler. When we try the controller functions, then it violates the safety because it doesn't have any the robustness or the adaptations on the method. However, when you try the rest of things, it looks quite well. It looks quite working well. So we confirmed that our framework can provide some tools to ensure the safety guarantees. And then the next one is the input delay. So if we have an input delay in the system, then we cannot ensure the safety guarantees. So we need to consider the input delay as well to ensure the safety guarantees. So this is the underlying ideas. This work is also a collaboration with the Aerodynamics Lab as well. If we have the equations number 1, this is our system. And then if we have a delay estimation, then we're going to use these equations, and then we're going to ensure the safety guarantees based on these equations. How can we do that? We can use the delay estimations proposed by Miroslav Kristev's lab. We can design the cost functions to estimate the delay. How can we do that? We can predict the state from the past to the current, just based on integral, if the system is forward complete. And then we can combine between the current measurement and the predicted one, and then we can use the gradient descent method to estimate the delay. So it is proven with stability from the previous paper. And then to compensate the delay impact, we can use a state prediction feedback controller. And here we use the state prediction for the future. But if we use a delay estimation, then we don't know the delay until the delay is estimated, until the delay converges to the true delay. So we're going to have an error in here. So the basic idea is that we're going to put the robustnesses against these errors into the controller functions. Then we can ensure the safety. This is proposal 1. If we generate the control input satisfying this constraint, I mean d of t, as you can see in here, that there is error terms in here, then we can ensure the safety guarantees. This is the worst case safety guarantees. So we applied our method, delay at the controller functions, into the model that used in the previous research work. Let's say we want to keep the safe distance here. And then there is a communication delay between two vehicles, something like that. And then this is the previous one. They assume that they know the input delay previously, and that it didn't work well. But our method, as we already expected, we can ensure the safety in a robust way, as well as the input delay is estimated over time. So next questions, you probably expected, how can we reduce this gap? How can we reduce these conservatisms? So because this is the worst case safety guarantees. So we have a delay estimator. We have a delay to control variable functions now. And then we thought that we can think of impact of input delay as a disturbance of the system. Then we have a very good weapon to fight against the disturbances, disturbance observers in a classical way. But the problem is that how can we combine the disturbance observers with the delay to control function? There are tons of methods, the combinations, disturbance observer and the control functions in the world. But if we have an input delay, then to the best of knowledge, we couldn't find any the references over there. So the basic idea, before going into our method, I'm going to remind you of the previous one. So we have a maximum delay estimation error bound, and then we can have a maximum state prediction error bound, and then we can achieve the robust control in the previous work. So our idea is that what if we estimate the maximum delay estimation error bound, and then we can reduce the maximum state prediction error bound, and then we can reduce the robustness. And then, as I mentioned earlier, we can also use the disturbances estimation error bound from the system. Now, the core idea is that how can we connect between two things? So we're going to propose some algorithms to update input delay, lower bound and upper bound, and then we can estimate the maximum delay estimation error and then reduce the robustness. So I will give you some equations. We have some control F system like this. And then, of course, we need to have some assumptions that disturbances should be bounded. It's just a normal one. And then if we use a nonlinear disturbance observers, then we're going to have a disturbance estimation error bound here. And then the EP of D is the state prediction from the past to the current. And then it should be bounded from the disturbance estimation error bound. And this is the overview of our framework. We have a nominal controller, we have a system, and then we have the estimation, and also we have a nonlinear disturbance observers. And then we propose the online adaptive update of input delay bound here. So this is a lower bound, this is the upper bound. And then we design the constraint like this. I will give you a detailed explanation. This is the bound of state prediction from the past to the current. We know the information, everything here. And then the B means bound of state prediction error with delay estimation. And then this is the bound of disturbance observer. Then the input delay should satisfy this constraint. And also, we hate the bouncing safety set because we have a bouncing safety set and we are not going to ensure the safety guarantees. So this is to avoid the bouncing safety set. And then we can have the lower bound, upper bound of the input delay, and then we can have the maximum delay estimation error, and then we can also have the maximum state prediction error bound, and then we can update the DOT here. And then this is the result. As you can see in this graph, we can reduce the bound of delay estimation error, and then as you can see in here, compared to previous ones, we can reduce the safety. We can reduce the conservatism compared to the previous one. So you can also see the papers via the QR code, and then this is gonna be presented in this conference. If you want to listen to the detailed proof then you can come to my presentation if you have time. All right, the last one is about the medical robotics. So in this slide, I will present the model-free controller functions for robotic systems. It's a very ironic, but it's published in the journal. And then we do not want to make the control design complicated, but we still want to ensure safety. So we have simple PID, we have simple QP, and then if we have a stable velocity controller in the robots, which is a well-established controller in a commercial robotics, and also we can make the stable velocity controllers in our robot as well in a simple way, and then we can ensure the safety. So as you can see in these block diagrams, so this is the normally we have the controller in our robot. Then we can design this quadratic program to generate the safe velocity. Then we can ensure the safety like this. So I will give you detail about the medical robotics. So we want to automate the robots, the endoscopic robots for the large intestine, the operation here. We want to remove the tumors without any damaging it and the neighborhood of tumors, because it's very important to preserve the tumors as pure as possible, because we need to check if the tumor is bad or not. So that's why we propose this method. And then this is the framework of procedures. So we can detect the tumors, and then we can define the safety set. And for some reasons, the robot trajectory could be wrong due to the human operator if we use the teleoperation like Da Vinci robots, or due to the vision of collisions, something like that. And then if we have the unsafe trajectory here, and then we can avoid the damaging the tumors. So this work, we just apply the model-free controller functions into the medical robotics because we have a very complex robot dynamics in the medical robotics, because normally the medical robot is operated by the tendon-driven. So this is the simulation work. Simulation result, we have 2 tumors, and then we have an unsafe trajectory, and then we can try some different parameters, and then we can remove the tumors without any safety violation here. Of course, we also tried to use the depth constraint, but as we already expected, it works well in the depth constraint as well. So this is also the first attempt to use the controller function in the medical robotics. So I was very surprised because safety is very important in medical robotics, but no one used the controller functions in the medical robotics. So this is the point. And then I will provide the conclusions. What should we take from your presentation? So we can recognize rigorous safety proof. We have one of the tools, such as controller functions. And then we can check out high scalability of using controller functions still in various applications. And then I encourage you to use the controller functions as basic controllers in your applications. You can see the summary of our research work, and also you can see all the papers in each sections via QR code. If you are interested, you can visit the site, and then please take a look at that. And then I will say the better safe than sorry. Yeah. Thank you for your attention. Thank you. Yes. Sorry.
How do you define the control barrier function itself? Do you use safety limits? And my second question is that QB problem is always recursive with physical.
Yeah. That's a good questions. So we define the controller functions based on the users. Let's say we can define the distance between the obstacles and robots. But the next question is very difficult, because we need to know we need to do the analysis of all states, all shape set, if we want to know the feasibility and feasible or not in the QP problem. So it's a very, very difficult question. But I mean, normally, if we want to solve the problems in the QP, we would say we just believe the QP, right? I mean, we also have the proof of the getting some solutions. But yeah, that's my answer. Yeah.
If the zero level set of the control barrier function is not a control invariant set, then
Sorry?
if the zero level set of the control barrier function is not a control invariant set, then we cannot guarantee safety anymore.
Okay, so
If you get back to slide 2.
yeah, the theorem 1, I guess. Theorem 1.
Maybe in the beginning.
I can go to just a moment. Yeah, I also would like to know though, how can we get the feasible set always when you use the control barrier functions? I'm finding that solutions at the moment as well. Yeah. So. Yes, this one.
The set S.
Yes. So this constraint, right? If we don't have any uncertainty in the systems, and then the h of x never hit the 0. When you see these figures, this is the first ordinary difference equation, right? H of x never hit the 0, so that's why we use this constraint in the control barrier function, right? Is that okay? I mean, does anyone knows about these answers? I mean, normally we use we just put the constraint with the control barrier function in the quadratic programming, and then we believe that that's going to be the optimal solutions, right? But we don't know that, right? Yeah.
Just a remark on that. So it's really a standing problem, right?
Yes.
To assess the feasibility of CP problem beforehand, and that somewhere is being investigated by people who work in reachability areas.
Yes, exactly.
To assess offline or beforehand.
Yes. Yeah.
Visual sets.
Hamilton.
May
Yeah.
ensure feasibility in some sense, but if I can pose a question. So I had a similar question in the same spirit. So it's very, thank you for the presentation, and especially the last parts really ignited some interests in me on model-free CBS.
Yeah.
So one of the challenges we are facing, especially in the model-free paradigm, is to assess the relative degree of the QP of the constraint beforehand. So if the relative degree is not 1, well, we are not sure if we are
That's
what
true.
kind of CBF we are going to construct, or we're not sure what kind of QP it's going to be, even if it's going to be QP or nonlinear.
Yeah.
So those are the challenges for us. So I just wanted to know your opinion. The model free is.
The model free is based on the relative degree 1. Yeah.
If you don't know the system, how do you?
Yeah.
That relative degree would be 1.
That's a very good question. But
Chicken and egg kind of problem.
But I haven't. But that's a very good comment, because that's why they designed the scenario with the velocity and the distance, right? Then this is the relative degree 1. So I haven't seen any papers about your question. Yeah.
The statement is easy, but the constraint itself, you're not sure if you will have access to the control in a linear way. But that's a challenge.
Okay. Yeah. It could be nonlinear, right? Yes, that's true.
So initially I wanted to talk about decentralized learning of equilibria, but we have some new results about safety in RL, and I was excited to share the latest work, and I think it also fits well with the safety thing. And we also will have a couple of talks on Friday about equilibrium multi-agent games. Okay, let's see this. So before we get started, I'd just like to start with a hope for peace and safety for everyone, given these challenging times that we are facing. Okay, so some of the applications that motivate our work include autonomous driving. So here you see our lab. We have robots where we can implement our algorithms and test whether the robot and the cars can avoid each other. So here collision avoidance is an important safety issue. We also work on robotic construction. So this is a work with architects where we are using robots to come up with creative structures to build. I can use this one if you, yeah. And so again, if here at the moment, these are at small scale and robots just in very confined environment, but if we want the robots to collaborate with humans, safety becomes increasingly more important. Okay, sorry, there seems to be a technical.
You can use this one.
Thank you. Is this working? Okay, and then another application we work on is robotic manipulation. So robots that can help humans do automated disassembly of battery disassembly or dexterous manipulation. And again, so far everything is sort of in confined environment, but we need robots to have collision avoidance and be safe with respect to each other and the humans. So a framework that we use for modeling all these systems is a stochastic control framework where the state x at time t+1 is a sample from a probability distribution which depends on the state at time t and input at time t. And a classical problem in stochastic control is to determine the input sequence that minimizes a running cost c of xtut. And classically, we know that dynamic programming characterizes the optimal solution to this problem. So it gives us a set of optimality conditions to find a policy, which is the mapping from the state to the actions. And it states that this policy, looking at this time history independent policies, is optimal and we can solve for them. And over the past 7 decades, our community has made a lot of progress in dynamic programming, such as addressing more general objectives, safety reachability, multi-agent formulations, and a lot of effort on computational tractability, such as approximate dynamic programming algorithms. Here you see an example of aircraft trajectory planning that we worked on. So this is a stochastic weathers. We worked with meteorologists to model stormy regions as a stochastic locations and then plan a trajectory deviation that's fuel efficient and also maximizes safety of the aircraft. But a limitation in dynamic programming is that computationally it's not very tractable and it's also very hard to incorporate real-time data. So we couldn't put 2 aircraft on this picture, our approach would break down. At the same time, we know reinforcement learning has been very successful in addressing complex decision-making problems, such as chess, Go, StarCraft, protein design, and so on. And here in the RL framework, we are solving the same stochastic control problem, but we assume we don't know the model of the system, and we optimize pi by interacting with the system and observing trajectory of the system. But a key challenge for applying it to the real-world system is having some sort of a safety guarantee. And I want to talk about some of our latest results in our approach to, one approach to incorporate safety, but I want to also acknowledge that this is a well-studied, the importance is well known both in the RL community and in control community. You just heard a talk about barrier function approach, but there are also other approaches like learning-based model, predictive control, safety training, neural nets, and so on. So we just give one piece of puzzle, one approach to look at these safety problems that hopefully can help with our understanding of how we can address these problems. Okay, so now we come into finite horizon safety via reinforcement learning. And first, I want to talk a little bit about reinforcement learning. How are the objectives incorporated usually? So we can have different formulations, like a finite horizon objective, where we minimize the cost up to a finite time, an infinite horizon, so a discounted or average cost, and both of these methods ensure that this series is summable. So with a discount factor that's between 0 and 1, we ensure that we have a summable series, and we get some nice properties such as contrastivity retractability that help with analysis. But this discounted cost, which is the most common cost used in reinforcement learning, cannot ensure infinite horizon safety or stability. And I want to briefly talk about that because I think it's an important aspect, and maybe in our control community we're somewhat aware of this, but especially when I talk about to learning people, I like to focus on this aspect. The average cost can incorporate safety and reachability in infinite horizon, but learning is more challenging because we don't have this contraction property, this discounting. And so far, almost all the algorithms you find online in RL and Python packages and so on are for discounted cost. So let me talk a little bit about what are some challenges with discounting. So let's look at a linear quadratic control problem. This is classical, we know this problem. And here, let's say we put a discount factor. And it's not hard to come up with examples of systems. Here is a scalar system where if the discount factor is not sufficiently large, the controller would be will not make the closed-loop system stable. This is an example from this paper. Our colleagues, Roman Postoyan, has been working on this, and you see that you get A plus BK basically is greater than 1, and this system will diverge even though the infinite horizon cost is converging, because this is geometrically decreasing basically the norm of this sequence. And there are colleagues who work on how do you define the discounting so that your controller will be stabilizing, but these usually require you to know the model of the system, which is in contradiction with what we look at when we talk about reinforcement learning. And I just want to highlight it's also a problem, this instability, lack of stability guarantee is a problem with cost formulation. It's not a solution approach. So if we see inverted pendulums being stabilized with discounted costs, we don't really have any guarantees about this. So then the next question is, what about safety and reachability? So let me define safety in the control theoretic sense. So we say that trajectory, and this is infinite horizon trajectory, is safe if xt is always inside some safe sets, for example, collision-free set. And we say that the trajectory satisfies reachability if there exists some time such that xt reaches a goal set. Okay? So these safety and reachability are dual concepts. So we are talking about stochastic systems, and that's why I have probability of safety and probability of reachability, and that's what we want to maximize. But you can easily verify that these are complement events. So probability of safety plus probability of reaching safe complement adds up to 1. So we can get one from the other. So we can, if we solve for safety, we can also solve for reachability and so on. But there was also a recent result from colleagues from formal methods that proved that safety and reachability also cannot be cast as a discounted reward or cost. Okay? And basically they gave a proof with counterexample that no matter how you fix your discounted reward, you can find a transition kernel, a stochastic system, such that the optimal policy for reachability is different than the optimal policy corresponding to your reward. So you cannot have guarantees for safety or reachability if you use a discounted reward. And the way they construct this counterexample is that you make the probability transition such that it would take a very long time, but with probability 1 to reach a goal set. But because discounting forgets about future, long-term future, it will not find that policy. Okay, you can see more examples there. So what can we do? Well, we went back to look at a lot of examples that we work on in the lab, and what we noticed, whether it's robotics doing a task or autonomous cars doing a maneuver, we see that they're finite horizon, and we have some safety constraints. And because of that, we started looking at the finite horizon. Oh, now it's working. Finite horizon setting. I just paused to see if there are any questions so far. No? Okay, so here is our safety and reachability in finite horizon. Same definition. Let's just recap. So given a time horizon capital T, we say that system is safe, the trajectory is safe if xt is always in S, and it satisfies reachability if there exists a time that xt is in G, and it satisfies a reach avoid if xt little t is in the goal set for some little t, and at all prior times it's in the safe set but not goal set. Okay, and that's last one is the most general. So now, how did past works in reinforcement learning incorporate safety constraints? So we took a look at a lot of papers. This is Safety Gym. It's developed by OpenAI, and it's a Python environment for testing safety of different algorithms. And the way they formulate safety is basically usually these two approaches. Either you put a penalty for violation of the cost, so this W is your penalty, and this is indicator function of not being in the safe set, or they put a cumulative constraint threshold. And neither of these two approaches has any safety guarantee by nature. It's a heuristic. And you would also have to tune the weights or tune this threshold manually to figure out how safe your system is. And so the problem that we focused on solving is that we want to solve a finite rise and a stochastic control problem, but we want to make sure probability of our trajectory satisfying reach avoid, so at some point reaching the goal set and at all prior times being in the safe set to be greater than some desired threshold 1 minus delta. Okay? So this is what we would like to solve, and we want to do it in a model-free reinforcement learning way. So the formulation of reach avoid is not new. It goes back to Abate, Prandini, Sastry in 2008. Then we had Summers and Ligouros also looked at this problem, and I worked on it when I was a postdoc. And also some new results and algorithms, but all of these approaches were model-based. And what we wanted to address was model-free reinforcement learning approach to solve this problem. And this is a work with one of my current students, Ting-Ting Ni, and one of my former PhD students, Ilnura Osmanova, and some collaborators. And it appeared in these works, the latest one being the HSCC conference, which exactly looked at the reach avoid constraint. Are there any questions so far? Okay, so if the problem formulation is clear, then I talk about our approach to solve it. At first, I want to give a little bit of intuition about the solution to this problem. And for that, we can look at different classes of policies. So we can define history at time t, which is the sequence of states and inputs our system experience up to time t. And if we have a stochastic policy, which is a probability distribution on the actions, a history-dependent policy is one where pi t looks at the history and gives us a probability distribution on actions. Okay, we can have a Markovian policy, which means that it's sufficient to just look at the last states. We don't need to look at all the history, like the LQ system. Okay, and we call the policy furthermore stationary if pi. So it doesn't depend on time. And this is the case if we have an infinite horizon discounted problem. And that's why many people look at this class of problems. It just simplifies things apart from the contraction property. So now let's look at a constrained Markov decision problem, which is closest to our setting, where we are minimizing running costs subject to the same type of cost, like an additive cost, being below some threshold. This is a well-known framework. It's called CMDP. And we know that the optimal policy in this case is Markov, so it doesn't need the history. And if we don't have any constraints, we also know that optimal policy is deterministic, whereas as soon as we have constraints, the optimal policy will be generally stochastic. And the intuition is that once we have constraints, the controller tries to balance performance with constraint satisfaction, and it might be necessary to randomize. Okay. What about our reach avoid constraint MDP? So it turns out that it's easy to create examples where we see that Markov policies will not be enough. And this is, I worked out the example. We have it in the appendix and in our paper. But let me briefly give you an overview. So here we have the green are the safe sets. It's just a 6-state MDP. We have a cost on state E that we want to minimize, so we like to minimize the probability of going to that state. U0 and U1 are control action, and from A, it goes the system without any control transition with some probability to B, which is safe, or 1 minus P, which is unsafe. And we want to have the probability of safety above a threshold. And it turns out that in this case, the optimal policy is history dependent. And the intuition is that the controller, because it has a budget on the safety, on probability of safety, it needs to know which path was taken to know how much it can, with which probability it can choose E versus F. That's the intuition. Because this constraint, P of X 0, 1, 2, 3 in the safe set is coupling the entire trajectory of the system. It's not a stage-wise cost. Okay? So generally, it's history dependent, which is not good. We're not very happy with it because we cannot keep track of a long history. It would be difficult to design a controller that's history dependent. So the next thing we did was try to reformulate the problem to cast it as a CMDP. Let me just pause and see if there are any questions so far. Okay. All right, so I'll just give you about how can we formulate a CMDP to model this problem. And the idea is to introduce an automata, a few additional discrete states that capture what has our trajectory done so far. So this Q has 3 states. Q0 is if you reach the safe set complement, so you become, so here this is the best to see it here. We start in Q1, the first state. As long as we are in safe set but not in the goal set, we remain there. As soon as we go to the safe set complement, we go to state 0 and we stay there forever. We became unsafe and we don't get out of it. And if we go to the goal set, then we transition to state 2. So it's a finite state machine. And if now we look at our new state space being product of the original state and Q, we can also define transition probability on this new state space. XT plus 1 is as before, and QT plus 1, the state of this automata, is determined both by the state of the original system and QT. Okay. And you can already see that our reach avoid objective can be seen as requirement that we reach state 2 because we want to be safe at all times and at some point reach state 2 in this queue. Okay? And so that's exactly how we reformulate the problem. So we say that x1 to t is in the satisfies the reach avoid constraints if and only if qt is 2. And so we can formulate a final cost, which is an indicator function on the qt, and this is exactly the expected value of this is exactly the probability of being satisfying reach avoid. And so now we have, and our original cost remains for the problem. So now we have a reformulation. This was our original problem. For the sake of notation, I combined the last stage cost with the initial cost for just compactness. This was what we wanted to solve, probability of trajectory satisfying reach avoid greater than 1 minus delta, and now we formulate it as an expectation of a time varying cost. In this particular case, it just has a cost on the last state, the state of the automata. So we formulate the original problem as a constrained Markov decision process on the extended state space. Okay. And also, it follows, because this right-hand side is a CMDP, we know that the optimal policies are Markov, so it suffices to consider Markov policies here, and we can map them. Basically, once we solve for the optimal solution there, we can map it to history-dependent policies in the original space. Okay. Any questions? Yeah? Sorry? Yes. In this particular problem, it just has 3 states. It's a discrete state machine. So it goes from 0, 1 to 2, depending on where the trajectory is. If you have, this is also a trick that people in formal methods use a lot. So if you have a temporal logic specification or other type of specification, you can formulate an automata. For example, you want to visit set A, then B, then C, and so on. Then you can make this finite state machine and map that problem to a reachability problem. So this Q would have finitely many states. That, But three finite state is not allowed to add to the original. X is the largest state space that is more challenging. So X is generally our continuous state dimension, could be the car position of cars and their velocities and so on. But this Q is more like a fake state that we made so that we can map the problem to something we know how to solve, at least model based. Does it make sense? Yeah. Okay, good.
My question is, maybe you will introduce it later on, but so if initially you have a continuous state space, so you automatically convert it to a discrete time space?
No, because the X hasn't changed, right? X is still in the original space, and now we just took the product space of X with Q.
But Q is discrete.
Q is discrete.
So in the end, your MDP will be in a discrete.
It will be in a hybrid state.
Yeah.
So X times Q, exactly. X can be continuous, can be discrete, can be anything. Yeah.
Because of Q, it becomes hybrid.
Exactly. Yeah. That's why we also publish in the hybrid system community, that one. Okay, other questions? Okay, so we have a CMDP on this extended state space constraint Markov decision process. It's more studied, but we still don't know like a reinforcement learning approach to solve it and have safety guarantees. So now that's what I want to talk about and share some of the things we have been learning in this RL approach to the problem we developed. Okay, so we want to find the optimal pi, which is now Markov, doesn't depend on history, but it's a function of X and Q to solve the following problem. And this is a final cost constraint. And our data is trajectory of the system. We apply a policy, we look at the system trajectory, and want to make sure that during the learning, safety is guaranteed. Because a lot of also past works, they ensure they might have safety guarantees after convergence. If we are really interacting with the real system, we want to also make sure that during the learning, we have this ridge avoid with high probability. The system is stochastic, so we cannot have it with certainty. And this is the model-free approach. The idea is that we parameterize the policy. We have time-varying policies because we have a finite horizon problem. So generally, the optimal solution is time-varying, but Markov. We parameterize, so we have a set of parameters, theta t, for each of the time steps. And we want to minimize this cost subject to these constraints. And this is really the constraints are what makes it challenging and different than the past work. And as I mentioned, we implement the policy, we observe the trajectory of the system, and then we want to update theta k at the next round, theta k plus 1. So let me briefly also talk about policy parameterization. This is used in RL a lot. We are mostly familiar probably with linear policies, where theta, where our policy would be theta transpose. In this case, it's linear-like because in Q it cannot be linear, it's a finite state, but theta transpose X plus some noise. And this noise is needed in RL because it's an exploration. It helps us explore. If we have a deterministic policy, we may not be able to have guarantees. The other class of policies that are more often used, one of them is Gaussian neural net, which it means that pi theta is from a normal Gaussian distribution, but the mean of that distribution is given by a neural net, parameterized by theta. It's a function of X and Q parameterized by theta, and we're trying to learn that theta. And the variance can also be parameterized. For simplicity, I just put it constant, but the main point is that variance shouldn't be vanishing, so we are exploring. And so on. There are many other classes of policies that in RL they're used. But once we parameterize our problem, the search over infinite dimensional function space of policies becomes search over finite dimensional parameter. Okay? Because now our unknown is just theta. And so this problem, our unknown is just theta, and this is in dimension t times d, if we have for each time step a parameter. And so it becomes equivalent to a constraint optimization problem, okay? Where the objective constraints are a function of this theta. Okay, any questions? Yeah?
I'm wondering how does
Yeah, we will see that. Yeah, good. Thanks. Other questions? Okay. So because we don't know the dynamics, we are in a model-free setting, it follows that we cannot compute those expectations, and these J and C are unknown functions. Okay, so we are solving a black box constraint optimization problem, but we want to design this theta k sequence such that C of theta k is less than or equal to 0, meaning constraints are satisfied with high probability, and pi of theta k, the policy parameter, goes towards the optimal policy. So this is, and the kind of approach we will give is like a gradient descent type approach. You start from theta 0 and you move in direction of gradients, but you don't know the gradients, and you estimate them, and we hope to reach that desired theta star, but also we don't know our feasible region. So everything is unknown, and we have to use basically black box, develop approaches for black box constraint optimization. On top of that, J and C are generally non-convex. Okay. So now I will highlight, give a high-level description of the approach. So the first step is we design a barrier to stay inside the feasible set. So this is like a function that, this is from interior point methods in optimization. It grows to infinity as you get close to the boundary of the set. Then we use system trajectory to estimate gradients and find the descent direction. And then we take a carefully chosen step in the descent direction. So I will briefly talk about each of these steps. So this is the high-level idea that we're going to do. So it will be a modified gradient descent approach. Okay. So let's talk about the barrier. So here it's the logarithmic barrier of the constraint. So there can be other barriers, but we just chose log barrier. So it's a function that grows to infinity if C of theta comes near 0 from below 0. Okay? So it's an interior point method. You start with a feasible point, and it helps you stay in the feasible point. And so our constraint optimization problem now becomes like an unconstrained optimization. We want to minimize J tilde of theta, where J tilde is the original objective minus eta log barrier parameter times this basically log barrier parameter. And we know that as eta goes to 0, the solution to J tilde, theta star for J tilde, goes to theta star for the constraint optimization problem. So now we want to do the following, do a gradient descent, but using gradient of the log barrier. And let's for a moment so let's see what are the questions we should be asking. First, would this approach converge to the optimal policy parameter? Given that J and C are non-convex, can we have some guarantees? Then, given that we don't know J and C, how do we construct good estimate of log barrier gradient, and how to choose the step size for safety and convergence? Okay. Any questions? So let's briefly talk about this, so solve these three problems. Okay. Oops. Okay, so the first insight is that this J tilde has a property that's based on the policy parameterization that's called gradient dominance. And what this is saying is that, let's forget for a moment about this eta. What this says that if the gradient becomes 0, we have J of theta less than or equal to J of theta star, so it must be that theta is an optimal solution. So stationary points are optimal. But we have an eta, so this implies that the stationary points are nearly optimal. You may have multiple stationary points. As an example of the function, this is x squared plus 3 sine x squared. It's a function that has this gradient dominance, so you may have multiple stationary points, but they all have stationary points are nearly optimal. So then the question is, how can we ensure this nu is greater than 0? And this relates to a property of policy parameterization, which is called Fisher non-degeneracy. It's used in RL a lot, and we can understand what's the use of it when we look at that, when we try to prove convergence. So what it's saying is expected value of gradient of logarithm of our policy with respect to policy parameter. And then this other term is the same thing but transpose. This has to be greater than or equal to some lower bound, it should be lower bounded by a positive definite matrix. Okay. This is like an exploration property. So then, for example, in our Gaussian example, if covariance is not vanishing, we have that covariance matrix eigenvalue, smallest eigenvalue would be on the right-hand side here, okay? So the intuition is not, the more randomness in the policy, the higher will be this mu f. And this mu f exactly relates to that gradient dominance. So then when we put this together, if our policy is smooth and Fisher non-degenerate, as we just defined, then we have this approximate gradient dominance. So this is that gradient term with some factor that depends on time horizon, mu f in the bottom, and the smoothness, the eta is from log barrier. And then the last term I want to focus a bit on is this epsilon bias. Just to give intuition about this. This talks about the richness of the policy class, because rather than searching in the entire class of policies, we are searching in the space of policies parameterized by linear or Gaussian and so on. So this epsilon bias is 0 if our optimal policy is in the class we are searching. And it becomes small where our policy class we're searching becomes rich. For example, in a neural network, as the depth increases, the epsilon bias decreases. This has been shown in some past work. Okay, so what this implies is that stationary points are optimal. That's good. The next order of business is to create a gradient estimator. Let me just pause to see if there are any questions. Okay. So I briefly also highlight the gradient estimation approach. So this is the gradient of the log barrier. It has the gradient of the original function, and this just comes from gradient of the logarithm of c. And we don't know j and c, but for the cost and constraint, because they're expected value, we can estimate their values using sample average, because it's expectation, so you can do Monte Carlo sample average estimation of expected value. Okay. To estimate the gradients of them, we need to use the so-called policy gradient theorem from RL, and we modify it for our case. So how many people have heard of policy gradient theorem? Just a couple. I briefly just highlighted to give an idea about how this works. Briefly again. If we define a cost to go, which is the expected value of our cost function starting from time little t to end, so this is cost to go. Then policy gradient theorem says that the gradient of j is sum over all time steps of expected value of gradient of the policy with respect to parameter times the cost to go. This theorem is very powerful because it says gradient can be computed as an expected value. And whenever we have expected value, we can use Monte Carlo sampling to estimate it. And that's exactly then what we do. We use then sample trajectories, n of them, to estimate that expectation. Because we know our policy parameter, we can compute this gradient and plug in the numbers. And we can also use the empirical cost to go and do this n times, and we get some estimate of it. Similarly, for estimate of the gradient of c of theta, and then once we put this together, we have a result about how many samples we need, little n, to be able to estimate gradient of the log barrier with some desired accuracy epsilon. So what this result is saying is that if we want our estimated gradient, this hat, to be within epsilon of true gradient with confidence 1 minus alpha, this is the number of samples we need. Okay. So we can get some theoretical guarantees with this. Now we have a very good control over our estimator properties. Does it depend on the horizon? It doesn't look like it, right? It's a good question. It should show up somewhere. Actually, it's a good question. Maybe I have to double check because I think it should depend on the horizon. I will double check. Maybe I'm missing a term there. Thank you. Yes. This is the other good question. So here we're assuming we have like a finite horizon maneuver. Let's say the car has to make a left turn and we cannot wait forever. Maybe it has to complete the left turn in 10 seconds. Or the robots have to complete some maneuver, and so we define some ending time for it. It's in some sense conservative, exactly. Yeah, but this is also a good question. This is kind of sort of open problem, same in MPC approach. How do you define that end horizon? Yeah, so we try to handle the problems, to move away from infinite horizon that has its own problems and look at a finite horizon problem that we can have theoretical guarantees, but deciding that time horizon, there's not like one true answer for it, and we have an upper bound maybe on how long the maneuver should take, but there could be maybe better ways to estimate. Yeah, good. Is it conservative? Okay, you will see that it's very, very large. I don't know if it's conservative. I don't know if we can make it tighter, but the point is that it's very large. So, and that's one of the challenges with these theoretical proofs that I will highlight. First, if epsilon is 0.01, this would mean 10,000 samples. C of theta is the constraint value, which means that if you're getting close to the boundary, you would need more and more samples because you need more accurate estimator. So it is very large. But I will exactly comment about that. I'll just talk about the step size briefly and just give a high-level idea. So that from optimization, we know that the step size should be sufficiently large to make a progress, but for safety, it has to be sufficiently small because we know we are currently safe and we only know our function around the point we have measured, so it has to be very small to stay there. But we don't know the function, so how do we determine how large it can be? And at a high level, I can say that we basically estimate a quadratic upper bound locally around the points we measured, and that quadratic upper bound gives us both a smoothness constant and also a region where we can say with high confidence we will have safety if we limit the step size. And then putting all of this together, this is our algorithm. So this is a black box. We don't have the model. Pi theta k is our policy given the current parameter. We implement several times to get the system trajectory and samples. From that, we estimate the gradients, and we update theta k plus 1. And then with suitable choices of a step size, which I gave some intuition, and this eta log value parameter, we have that policy satisfies constraint with high probability at every time step during the learning. And we also have convergence, so we are at the last iterate t, we are within epsilon of j of pi star, so cost of the optimal policy, with t being of order 1 over epsilon squared, and n being of order approximately 1 over epsilon to the 4 samples per trajectory. Okay. And this was, initially we looked at this for just a simple black box optimization. That was the first, so that was the history of the problem without even RL. And then with my student, we generalized it first to discounted infinite horizon RL, and then to the reach avoid RL to have somehow the most complete theory for now on this problem. But as you pointed out, what can we say? It's good, we have some guarantees, but this N is very large. It's almost impractical for real systems, so we are also implementing on benchmarks and real world, but I just highlight this is the OpenAI safety gym. There's a robot, red robot. We don't know its dynamics. it's like a black box as far as we can say. The controller is parameterized by some neural network, and we are basically using our safe learning approach to, it has to reach this green set, which already a priori doesn't know where it is. It has to avoid all kinds of obstacles in the environment whose location it doesn't know, and it just learns by interacting. So what can we see? The blue is our algorithm, and we can see that in terms of constraint violation, it's doing better than that state of the art that time when we compare it with. The literature moves fast, but it's much better in terms of constraint violation. So it's even this dashed line shows that when the task changes, it still maintains safety, whereas other approaches might lose safety before they come back. In terms of the reward it obtains, it's much, much slower, and this is also because of this conservativeness, because if you want to be safe, you're much more conservative. So it explores very, very carefully the environment. It's much slower to find that in terms of getting to that green circle and finding its way. And so this is, yeah, you have a question? Yeah. Yeah. Yeah, yeah, I was very fast about this. So we built a quadratic upper bound on the function. So this quadratic curvature is like a smoothness constant, local smoothness constant. So if you choose gamma to be 1 over m, that is smoothness constant, it helps to be fast enough. But also, this quadratic upper bound then gives us an upper bound on how fast it should be. So because you know that if this is the constraint function, and you want to be within certain distance to the 0, then it gives you a range on so how should gamma step size be. So basically this is your next feasible step, okay? Does it make sense? Yeah. So it's mean of basically 1 over that smoothness, and then some term that depends on this, feasible region based on the quadratic.
And I guess the m constant m.
We estimate it, yeah. Yes, exactly. But we estimate it because we don't know J and C. Yeah. Okay. And another point, but generally, I think my takeaway from a lot of these RL methods is incredibly sample inefficient. So for this problem, even without our safety approach, you need of order of 10 to the 5 interactions with the environment, and then 10 to the 6, 1 million interactions. Clearly, we cannot do this in the real world, right? But it's a model-free approach, and we just don't assume we know anything about the systems. And this is, I guess this is a price we have to pay. So maybe a better way for real practical impact would be to compare model-based and model-free. And most recently, we are also implementing this currently just in simulation, but they're translating to the lab, where these are trajectories that come out of this approach. The initial conditions are spread, they're from a distribution in our feasible region, and they need to find an exit safely. And this is learning this by basically running a lot of simulation. Okay, it's towards the end. So what are some takeaway messages? I started by talking about different cost formulations, and that infinite horizon discounted cost or constraints don't have any stability or safety guarantees. They might work well in practice, but we cannot have guarantees. We developed a method that had finite horizon safety and reachability guarantees in a model-free way. And this can help having some trust in applying this in safety-critical system, but a catch is that sample complexity is very, very high. We need a lot of interactions. So my sort of takeaway is, if we can model the system, if we know we have a good idea of the model, if a linear quadratic controller would be good enough, let's not try to use these methods. But if for some really tasks that our traditional control cannot approach, such as manipulations and so on, then these RL approaches would be more useful, but still we would probably need to combine model-based and model-free. And currently we are trying to verify these methods on real world, but we need to address sample complexity and sim to real transfer. Multi-agent system extension, so this is also a big topic in our lab. It's very fascinating. Once you have safety constraints, the problem of existence, computation, and learning equilibria become to a large extent unexplored. We just had some latest result with my student, Julio, who's here, and other students, but this was in a safety-constrained linear quadratic control problem, which interestingly, even that in a game setting wasn't explored much before, but we hope to go into more complex settings. So yeah, thank you very much for your attention, and I'd like to thank you. No, we don't make any assumptions. But basically, we don't choose them. They come out of they would be this expectation of this running cost. So they're determined by the running cost, by the dynamics, and by the policy, implicitly determined by that. So we don't make any assumptions about them.
So it could be a polynomial?
It could be anything. The only thing that we can show is that it has this gradient dominance property under some policy parameterization choice. Yeah. You're welcome.
These sets are compact sets. Do you have some?
For the theta, we know for safe set or we didn't have any compactness assumption because we get rid of this. Basically, everything comes into this policy parameter choice. So the search is now over the parameter space. So we have to think of how does what does the parameter space, how do the functions depend in this parameter space? We don't approximate the states. We are approximating policy. We are saying the policy parameterized by a neural net. Sure, but that part, so we just say theta transpose x. Think of a linear, right? We are just determining theta. X can be unbounded. X can be anything. Theta is the decision parameter. Yeah. Yeah. Okay. Thank you.